and we record to the computer to save the bandwidth. And so now we're going to turn it over to Mike. Take it away, Mike.
Thanks, Jim, and thanks all. Mike Barnett, as you said, from Cowtown Amateur Radio Club, and I drag along with me Mark Culross, KD5RXT, who is my cohort in crime for this particular project and a few other Cowtown projects. I've created this presentation. I probably need to give it to our club, but I may have more information than you need. I'm going to step through the slides. If you need me to cover something in more detail, by all means, let me know and I'll jump back into it. Because I'm not sure where people are, what people know about this particular system. So I'm talking about ham TV or digital amateur television on the ISS, the International Space Station. The Cowtown Club got involved in this because of member Keith Pugh, W5IU, who is now Silent Key. He originally proposed that the Cowtown Club build a ham TV receiver to retransmit these DATV downlinks from the ISS for use in school contacts, etc. He proposed it in 2017, collected some hardware, the transmitter failed in 2018, and then Keith left us in 2019. So the project kind of got slow rolled from that point. We are now finally able to say we've completed, or at least mostly completed, the project. I'm going to throw some terms out there kind of interchangeably. They kind of mean the same thing. Ham TV, DATV, ham video, they all involve digital amateur television. So it's amateur television, but it's digital form. So who's involved? NASA, obviously, they're all about promoting educational and public outreach. You have the European Space Agency, who was built in 1975 to allow European states to cooperate in space research and technology, and their tie-in with amateur radio is to allow school contacts. The ISS itself, occupancy began, easy for me to say, in 2000, and we all know the scheduled decommissioning is somewhere around 2030, although I just heard they're going to push it back maybe to 2035. AMSAT, Radio Amateur Satellite Corporation, came about in 1969 for educational outreach, etc. And finally, ARIS, Amateur Radio on the ISS. It's pretty much the collective of all amateur operations on the ISS. There's probably about 20 international amateur radio groups that are involved in ARIS. AMSAT's one of them. ARRL is one. Different European countries have different groups, but they all come to ARIS as the clearinghouse for everything involving ham radio on the ISS. So, original proposal to ARIS, and I'll probably keep throwing out AMSAT by accident, but original proposal to ARIS in 2000 was to have a transmitter so that during school contacts we could also transmit video. So you'd have the school contact radio using amateur radio and the school contact video using amateur radio. The antennas were pre-mounted on the exterior of the Columbus module. The Columbus module is part of the European Space Agency, and I'll tell more about that in a second. The module was launched on Atlantis in February of 2008. In 2013, the transmitter was finally installed. Between the initial proposal and the installation of the transmitter, they had to discuss whether they wanted to go regular analog amateur TV or digital amateur TV. They finally decided on digital amateur TV in the 2.4-ish gigahertz spectrum. In April 2014, they finally got the transmitter commissioned, and it had been doing test transmissions up to that point, but at 2014, they said now it's ready to go. 2019, the transmitter failed, and as you know, after 2019, we had COVID, everything else. The transmitter was downloaded from the ISS, sent back to the manufacturer, reworked, came over to ARIS, where Rainey Berger and his team of engineers tested it, built a filter pack for it, got approved from NASA, and then in March 2024, it was sent up on a resupply mission. Because of the way NASA operates and the ISS operates, The original spot that had the transmitter got used for something else, and now they needed plans for where to mount this transmitter. Well, it took a year before they finally got the plans and the checklist on how to mount the transmitter. And in July 25, it started transmitting a blank signal. Yeah, it's transmitting is a digital signal, so it's transmitting some digital information, but the video itself is just a black screen. The original installation, all they had were composite cameras. Well, by the time 2025 rolls around, it's all HDMI everywhere. So part of the planned upgrade process is this converter to convert the HDMI to what the AMSAT or the ham TV transmitter can use, as well as broadcasting color bars. So that's what we're seeing right now is we get color bar information with the digital identification string. Here's the transmitter. It's a lovely piece of gear. You can see all sorts of switches and plugs and stuff. That's to handle all the video modes as well as all the different audio modes and the two antennas. And who knows what else is on there. They over-engineered it. It's built by Kaiser Italia. It's a 5-watt transmitter. They had 4 frequencies they're playing with, but now they finally settled in on 2.395. We'll talk about Wi-Fi on our end, but they have Wi-Fi on the ISS that can also be a problem for them. And like I said, it's located on the Columbus laboratory module. If you're on the ISS and imagine your feet are pointing towards the Earth and your back is to the back wall of the Columbus module, the lower left is where the transmitter used to be mounted. I don't know where it's mounted now, but that was the original location. And you can see the hatch off in the distance, and that's the central corridor of the entire ISS. Here's a close-up of that mount on the floor, and there's Italian astronaut Samantha Cristoforetti showing it off. I don't know if she was involved in installation, but the timing is about right for that. And obviously, Italian transmitter, Italian astronaut. The Columbus module antennas were installed on the ground when the module was being assembled. And there you can see the guy, and you can tell by size, they're roughly about 18 inches. It's listed that they are both dual L-band and S-band antennas. I don't know if that is the original spec or if they really are dual-band antennas. We're only using the S-band portion of them. They are 10 dB gain antennas. They're right-hand circular polarized patch panels. They have basically a 180-degree radiation, what do you call it, signal or what? I can't think how you describe that, but they're from 180 off of the flat panel is where it's transmitting. They are not on the center line. They're actually after the center line where that technician is sitting. That is the aft part of the ISS. So they're slightly blocked. And I'll get to that a little bit later. Between the loss of the coax and the long runs, and then you have the 10 dB gain, they think they're getting 10 watts out of the system. Here's it located on the ISS. What they consider the front of the ISS is the direction it's traveling. So the arrow kind of shows what direction the ISS is traveling. Because of that, the Columbus module, circled in blue, is always on the south side. And I mentioned the antennas on the aft portion. So I think you can kind of already see that there can be some issues with blockage of the signal. Additionally, the ISS flies in a nose down attitude to protect the cupola from space debris. So they're even a little bit further back. So if you're standing on the Earth looking up at the ISS, to the right is the Columbus module. And again, the direction of orbit is that way. And the antennas are right there. So again, you can tell they're slightly aft of the center. And there's a zoom in of them, again, showing the direction of flight. And you can see that one's Eris number 41, and Eris 43 is the other one. So the reason I kept bringing up his location is this kind of what we're dealing with. This is exaggerated image, but we can pick up the ISS radio. We can at least hear it on the horizon. So the ISS is on the horizon. We can hear the audio all the way to the other horizon. That's using the dual band repeater. However, the video, we can't pick it up until it's reached a lot higher elevation. So they advertise about 20 degrees. For us, it's about 25 to 30 before we start getting a good video signal, just because of where it's located and some other mechanical obstructions. The signal we're trying to get, and I'm just showing this piece of software just to show the numbers, but it's 2.395 gigahertz. It's 200 symbols, sorry, 2,000 symbols per second. We have a down converter, so that's the offset frequency. If you look down, I don't know if you can see my mouse, but the lower center, there's a quadrant of like 4 clouds. That's depicting the quadrature phase shift keying. If we had a good signal, they would be tight little buttons of dots. Because we have kind of a weak signal still, they're big clouds. If you look over to the lower left, you can see the carrier. We have a good carrier frequency dialed in. We have a good symbol rate. RF receiving power could be better. And the next one over, and Mark could probably tell you exactly what this is, but the C/NMER is basically the quality of the signal, how much noise is on that signal. You can see the color bars. It says no signal because there's no camera hooked up to it. And other things it's shown is, what kind of data rate we're getting, that kind of thing. Even as it is, we're still getting good enough signal to decode video. Now it's a static signal, so we don't know if we have losses, if the signal is dropping out, but at certain points we're getting good signal. This is our test bed. Let's see. Forward error correction, 1/2, or 1 to 2. So what do you need to receive it? An antenna. You need some kind of amplification off the feed, just like you guys are already using, except it's in the 2.4 gigahertz band. Probably need a filter. Probably need an inline coax amp, depending on your installation. Some way to receive it hardware-wise, and then some software to decode it. This is our stream for data. So we have our commercial feed. We have our low noise amplifier, which is also a down converter. We have a standard inline cable amplifier, about 75 feet of cable to the bias T. The inline amplifier also passes the power. So both the down converter, I'm sorry, the LNA and the CATV amp are both powered off the same bias T. And then we have a split off. We actually have a three-way splitter. We have this hardware receiver hooked up to ports down, which I'll talk about. Another hardware receiver on that software I just showed you, and we have a SDR as a third connection. And we're using all three just so we can cross-check and see if one's getting a better signal or if we're having a problem. We're kind of still in the test phase. Receiver antenna, again, I bring up a weak signal, so you need as much gain as you can get. They recommend a 1.2 meter dish minimum reflector. Remember, it reverses polarity, so left-hand circular polarized feed. The ISS is right-hand circular polarized patch antenna. RF designs is what we're using for a commercial solution. However, Mark built without a reflector, just a transmitter antenna, right-hand circular polarized, so we could do some ground tests. And just using a 3D printed housing and some wire, and it works really good. So you don't have to buy a commercial setup. Our setup is on the roof on a 10-foot mast, so we kind of wanted something we could set and forget. The original plan, this is the original spec document. They recommend a parabolic antenna, the system wide being right-hand circular polarized, 26 dB of gain, a Azel rotor, accuracy of plus minus 2 degrees of the rotor if you have a 1.2 meter dish. The rotor has to be able to move at 5 degrees per second, a range of 0 to 180 degrees elevation. So that means all the way upside down, and 0 to 360 azimuth. You have to have some kind of tracking software to do all the math. And then the tracking software has to allow flip modes. You have to be able to go from one horizon to the other horizon without needing to rotate, just flip over top. This shows our setup on the roof. Like I said, it's on a 10-foot mast on a non-penetrating roof mount. And there's a zoom in of the antenna itself. Now, what we've added and what wasn't in that previous diagram is the piece of coax from the feed to that gray box. That's where we have put the filter that you guys built, and I'll talk about why those are necessary. So we have our feed, we have the filter, our low noise amplifier, and then the coax down to the clubhouse. Amps and filtering, again, weak signal. You have to amplify off the whatever feed you're using. I've got a bunch of notes. I'm going to skip a bunch, but they recommend, it's S-band is the frequency. They recommend 40 dB of gain, frequency stability of 20 kilohertz, and a noise figure of about 0.7 dB or lower. Long story short, nearby Wi-Fi can desensitize your LNA. We'd read that. We kind of thought it could be a problem. We didn't realize that what was happening until we started really looking at the signals. And the Wi-Fi was so loud that the LNA says, oh, you got plenty of signal. And I'll show you why it was doing that in a bit. And as soon as we added the filter, our whole life got better. Last little bit, they recommend inline CATV amp, especially if you have a long cable run or if you're using a tuner-based receiver versus a SDR. The tuner-based receivers are expecting so much dB input to begin with. Here's our LNA and down converter. And if you look at the input frequency, 2320 to 2450, that's why Wi-Fi was killing us. That's like the entire Wi-Fi band. It's being amplified by this. If you had a narrower band LNA, or perhaps it was further down in the 2.3 gigahertz band, it probably wouldn't be a problem. But because it was wideband, it's happily picking up the Wi-Fi and going, oh, you guys got plenty of signal. And then here's the filter you guys mocked up for us. This is not to scale. Our LNA is a lot smaller than it shows in the picture, but that's our whole receive setup. The optimal would be have the LNA on the feed and then the filter afterwards. But like I said, the Wi-Fi was killing our LNA, so we had to put the filter beforehand, before the LNA, and so we're losing a bit of signal right there, and that's still an issue we're working on. So how do you receive it? The original spec assumed you would have some off-the-shelf DVB-S satellite receiver slightly converted for this usage. Those DVB-S receivers are only good to 1.5 gigahertz, so you had to have a down converter. Again, the whole purpose of this was to share the video for school contacts. So if you had a standard off-the-shelf satellite receiver, you still had to have some way to capture the video and restream it. Later on, some smart folks built some custom DAV-TV receivers that just plug into your computer, sort of like an SDR. They have the same tuner guts, but you don't need to then recapture it. It's going straight into the capture string. If you don't, and the two examples are the Mini Tuner, it's French, and the Pico Tuner. And additionally, you can have an SDR. So we're using the ADLAM, sorry. I'll let Mark correct me on that. Pluto SDR. We've also tested the Lime SDR. Now, SDRs and the Pico Tuner, they all go to 2.4 gigahertz or above. It's only the Mini Tuner that was, sorry about that, stuck at 1.5 gigahertz. So the Mini Tuner, this was the first custom built receiver using the off-the-shelf tuner module called a network interface module. This was sold through BATC, the British Amateur Television Club, and ARIS for this purpose. Built by a Frenchman, Jean-Pierre Courjade, and I'm mispronouncing it, Fox 6 Delta Zulu Papa. This was sold in 2016, not available anymore. Uses custom software, so no other software can use it, and the software isn't available as well as that hardware isn't available. But we have one and it works, so we're going to keep on using it. This is the guts internally, and that silver box, what I'm talking about, the standard tuner or network interface module. That's what we kind of think of as a tuner, but that's what does the work. The rest of the hardware is to drive a bias T. It can be a bias T if you need, and also to take that data and put it out through USB, and that's the box on the lower portion of the screen is. And this is what that NIM is. I don't know if you guys play with these things. I didn't know what they were until we started researching this, but that's what it looks like. And the three different pieces of what we're using, and we take the straight data from that last portion and stream it through the computer. That's a network interface module. I'm not going to cover it in too much detail, but the three pieces, the front is the booster. The second part creates your I&Q signals, analog I&Q signals, and the third part then takes those signals through a QPSK demodulator, and that produces a transport stream that we're feeding out and running down the USB and out to the internets. SDRs were kind of the next thing after the mini tuner because there wasn't anything else available. We're using ADLAM, Pluto, and the Lime SDR. There's plenty of software available as well as the ports down 4, which I'll talk about. Pico Tuner came later on, in fact, just in 2024. It's another kit from the BATC website for BATC members, made by Michael Willis, Gulf Zero Mike Juliet Whiskey. Again, he used that NIM module. It can go to 2.4 gigahertz. It's called the Pico Tuners because it's using a Raspberry Pi Pico for the USB interface portion of it. Again, there's a bunch of different software that can use it as well as the ports down. So here's the software, the mini tuner, unavailable. Open Tuner is one that can use the Pico Tuner, and I think it can use some SDRs. I don't remember. SDR Console can use SDRs, and the side to it is SDR TV. Unfortunately, it only does the DVB-S2, and the ISS is DVB-S, different format. But we can still look at signals from it, and it's got a nice spectrum display for it. And finally, the ports down 4. And if I'm going too fast or have any questions, don't hesitate to stop me. And this, again, I already showed you. This is the mini tuner software, which matches up to that piece of hardware. And both of these are unavailable. This is the Open Tuner. This is the only screenshot I have. We don't have it hooked up. We don't have the Pico Tuner hooked up right now, so we're not to that computer, so we're not using it. But you can see you get the same information. It's showing the mode, the transport streams. You got all the data coming in, what your signal level is, and all that kind of stuff. And you notice all those tuners, the NIM modules, have 2 coax inputs. So you can actually run 2 different things into this. It's a dual tuner piece of software. And finally, the ports down. And I won't go into too much detail of this. I'm going to show some pictures of it. The background is Australia and Europe are big into digital amateur TV. Australia uses UHF VHF for it. And in Europe, they get to use a satellite. I think it's Emirates. Maybe it's Qatar. I think it's Qatar. Orbiting over Africa. It's a commercial satellite, but it has an amateur radio package of it in it, which has a 10 gigahertz and 2.5 gigahertz sections for use in digital amateur TV. So they are all the time be able to play digital amateur TV. So their systems are very well tested. And Australia does it all with terrestrial information. We're the only ones that don't see them do it at all. So if you look on the picture at the bottom, the frequencies they're using, that's because that's what the Australians are using. It's useful for us because as nice test equipment, you plug in, depending on the SDR you have, you plug it in and you can get different signal displays and that kind of thing. And what we're using it for, and this is showing some of the video portion, the software is designed to be a transmitter or a receiver. So this can run your transmitter depending on what you have plugged into the hardware, or it can be the receiver. It's a great piece of kit, and it runs on a Raspberry Pi 4 and a 7-inch touchscreen. And written by, I'm checking my notes, It came about in 2022 based on this project called RPITX, or Raspberry Pi Transmitter, written by Evariste Corjand, which is the same last name, the guy who made the mini tuner, and is from the same area of France, so maybe they're related. Fox 5, Oscar, Echo, Oscar. The key for us, the reason I'm showing this picture, the last screen, the lower right has ISS Ham TV receiver merger. So this is how we're using this. We select that, receive, start the stream, and now we can share the video to everybody else. And I'll kind of show the next portion of how that works. Again, going back to the original purpose was to share this video. Unfortunately, because of how hard it is to receive the video signal, you only get at best 4.5 minutes of video. We're getting about 3 minutes of video at best. The optimum is 4.5 minutes, roughly. The normal satellite contacts are about 10 to 12 minutes, depending on, or the normal ISS contacts on audio are 10 to 12 minutes. So in order to get longer video, they expect a number of different receivers during the orbit to keep handing down the video. And that's what the Aris Ham TV merger is. Again, done by the British Amateur Television Company or Club. If you look on the right, there's a bunch of receiver stations. They're all offline right now because nothing's being transmitted but the test signal. There's even one down there in Allentown, Pennsylvania, as well as all over Europe, Australia, and Japan. The way it works is that transport stream that we receive from the ISS, we send it on down through here, and they're all matched up. The streams, there's coded information in them, so they just match up the streams. And as one's losing it, the other can hand it off and pick it up. So you have one continuous video. That's the plan. Obviously, we don't have any video going right now. They've done one test, but that's how it's going to work. In the US, we need more of these receivers, obviously. There's ours, and there's one in Allentown. Not who else is working on them. In Europe, they're covered with them. But, so that's where we are on that portion of it. Results so far. So the first one is a picture some of you might have seen. This is from that Portsdown 4 software. And I superimposed what the frequency is, the actual receive frequency. Because with the transfer, the lower number, that's what we're actually tuning in. And you can see what we're trying to receive is at the low spot. There's a big peak out there in Wi-Fi. There's another peak down below that. I don't know what that is. With the addition of the filter, the lower signal, now these are superimposed, so the same dB range. The lower signal is the current, and the upper signal was the old. And you can see that the Wi-Fi signal came down about 5 dB. The signal we want dropped maybe 2 dB. Ignore that spike. I think that might be in the club. But you can see that other big signal is completely gone, which is kind of nice. Now, this is from a receiver in the club, unshielded receiver. So some of this signal, it's possible it could be locally generated. But for the most part, it's pretty good depiction of what we're getting. It's really hard for us to test this on the tower because of injecting power and that kind of thing. But you can kind of see that we've gained a ton. And I tuned it this 1478.8, which is slightly above what we're receiving, just so I could make sure there wasn't any DC offset in there. So just below the frequency we want, we're getting a big signal. And these are just noise floors. There's no transmitted signal during the screen capture. So our to-do list is to shorten the coax between the feed and the filter, and shorten the coax and filter the LNA. We kind of just mocked it up, and you probably saw the pictures from Jim of the setup. We just haven't gotten further than that to this point. Here's some links of stuff I talked about. RF ham design is where we got the antenna. The batc.org.uk is basically the spot to go for digital amateur television. There's numerous AMSAT spots that have detail about the ham TV system, but the Belgium one seems to be the best. And then that merger page is this live.aris.org/ham TV. How am I doing on time?
You're doing good. Just take as much time as you want.
If you want, I can show you a quick video, the important portion of the video that, let me see. I'm going to stop share just for a second. Here you go. So this is, you should be seeing a video on the screen. It's not playing right now, but you should be able to see the video. This is put together, captured off two different computers. We're just recording all the data we can get, so we can kind of get an idea of where we're going and how well we're doing. I paused the video at the point where we're starting to pick up the downlink. As you can see, we're about 29 degrees elevation. You can tell where the antennas are pointed. The ISS is north of us, which means the Columbus module is south, so it's closer to us, less fuselage blocking it. On the SDR television, you won't see a signal on there again because it's looking for DBS2, but you can look at the spectrum and watch it come up. The video is starting to show up in the mini tuner software. You'll start seeing the carrier coming up. You'll start seeing the symbol rate. And this is kind of what we're playing with. And let me see if I'm going to play the video. There's a thing in the way. We've heard
Okay,
audio.
we see things moving now.
Yep. So you can kind of see how quickly it's moving. And now if you look on that SDR TV, I'll mute the audio, you don't care about that. If you look at SDR TV, you can see we're seeing a signal there above the noise floor. It's just starting to pop up. The receiver software is still trying to drag something out of the weeds. It's searching for a signal. It knows it's there. It's just trying to fine tune on it. And this is one of the first ones we did after we got it connected. So now we got a pretty good signal showing up on the SDR television. There's our color bars. There's the data stream info. You can see on the right side, it's going to start showing color bars in a second. Capturing is kind of challenging through all this because sometimes the software doesn't like being captured. But you can see it's starting to pop in the mini tuner. And that's kind of why we run both, is we don't know which one's going to pick it up better for whatever reason. And there's our signal. And that's about as good as we're going to get. The DB, I don't have an apples to oranges comparison. And there's our quadrants now have popped in the four panels, the four clouds in there. And we'll receive a signal for a while. Now it's going to drop off and the video won't disappear. It kind of just buffers the signal. So if we just kind of look at the spectrum display on the SDR television, you can kind of tell when we stop receiving a signal at all. But if you just kind of watch the data flow on the right side of the mini tuner, that's kind of showing you if we're receiving something or not. Now you see these are short passes, and this was just one of the first ones I picked up that had information you could gather from. So now the ISIS is lowering again, and if you know where our club is, we're just north of downtown Fort Worth, so there's lots of buildings around us. So as we start losing elevation, we're going to start getting blockage from buildings. But we're already below where it picked up on the other side, and we're still getting a signal, again, because of where the antennas are mounted on the Columbus module. The mini tuner software is still getting a signal. It's fighting. It's still trying to decode something. It's starting to lose it. You can kind of see it dropping in and out. It's trying to pick it up. It really fights hard to try to decode the signal. It's pretty surprising how well it does. But you can see the SDR television spectrum display. It's showing it's still got a signal coming in that bandwidth. So it may be a noisy signal, but we're still getting the signal right there. And we're going to start losing the buildings here in a little bit. You can see it dropping off right there. And on the software wise, we stopped receiving the signal. And we're down at about 22 degrees. So that's been the challenge the whole time. And I'll stop sharing that. The challenge the whole time was that, if I can, was that we have such quick passes to try to capture this and figure out what's working, that it took quite a while, quite a lot of passes before we figured out where we were and what was working, what wasn't working. And we received nothing signal-wise, video-wise, until Jim showed up with that filter and we hooked it up. So what you're seeing now is a direct result of that filter. Can we use a better filter? And sure, we'll take a better filter if someone wants to work on one, but we're definitely heading the right direction. So that's kind of the gist of my presentation. So now I'd like to open it up for questions. I want to see his slides over again, or if you want to ask technical stuff, that's why Mark is here.
Jim,
Yep.
can you ask him if the filter is connected directly to the feed and then the LNA, or is the LNA precede the filter?
I think it's coaxed on both sides of the filter. The question, Mike, is where's the filter with respect to the feed horn and the LNA? Is there coax on both sides of it?
Yep, I heard the question. Good question. The proper way would be have our LNA right on the feed and then the filter after that. Because where the noise is, we have the filter on the feed and the LNA after that. So we're already losing a bit of signal from the feed through the filter, but we have to do that because of the nearby Wi-Fi.
Yeah, but there is a length of coax from the feed to the filter, right?
Yeah, right now we have too much coax. We're working on a plan to shorten all that or some more direct connections. But yeah, that's one of our limitations.
Filter.
The filter is first.
Yep.
Right. Okay. Other questions?
Hey,
We'll
feel
continue
free
to
to
search.
make your own systems.
Yeah, well, you need some more systems. So is the one station in New Jersey is the only other one besides Cowtown?
I didn't even know that one was around until I just saw it pop up on the screen. As we were talking to the BATC guys, they were excited that we're having that a U.S. Club was trying to build a station. So, as far as I know, we're the only two working on it. There may be others that are hiding, but as far as I know, a good location would be uh, like Washington State area and then Florida, and they would kind of cover the corners. But
Yeah. Yeah, well, the video was real engaging to, it illustrates the speed of the pass. You've got the signal showing up in the spectrum. You've got the decode showing and all the gauges moving to the right. And that was real engaging, is nearly as good as being there. I guess it's better than that because you can't see all that with one view.
yeah, that's what I'm just recording the passes so we can go back through and go, what happened. And we know consistently that for us to have a reception, the ISS has to be traveling north of us. If it's traveling south of us, we're going to have a very hard time getting the signal out.
Yeah. For one thing, a pass to the south you would encounter the downtown Fort Worth buildings.
That's part of it. They're actually more towards our east and southeast.
Yeah.
But the biggest portion is just the fuselage of the ISS as well as the solar panels. Depending on where the solar panels are arranged or are lined up for the sun, they're also blocking the signal.
Mm.
So there's a lot of challenges to receiving.
Yeah. Get it. We had one more question here, David.
Yeah, you the software where I can get outside the Wi-Fi band and receive the signals. I don't know if that's even possible, but I'm just curious if everybody looked at that.
I'm sorry, I only heard half the question. Can you repeat it?
What was the name of the software?
It was ubiquity. It's hardware they use to run Arden software on it, and they programmed it so it's on down, minus 2 channels at down in the Wi-Fi band. And I'm wondering if anybody's looked at that to receive this.
So is that the ISS transmissions that are 2 channels down?
Yeah, okay, I understand. We even have Arden antennas on our tower at the clubhouse, and so yeah, that was one of our concerns. I think we have them turned off now while we're doing this, but that'd be in the same range of what we're receiving, that 2.395 area.
I'm wondering if you could repurpose that hardware since, they write the Arden software. Could we write some software on that same hardware to receive these signals?
That is beyond my scope of knowledge. I would say probably not, just because of how how that software works.
So that was a Wi-Fi transceiver what they were using for the hard.
Yeah, they rewrote the software. They loaded custom software on that hardware, and it's channel -2, which is I think right in this frequency. Maybe figure out if we could write our own software to run right on the hardware.
An idea to look at. You have to look at the bandwidth that's needed. Plus, he mentioned that you're using 4 so that's incorporate that. But have to have a pretty good process. I have one of those receivers myself.
I got 5 or 6 of them and a dish. Yeah.
Okay, Mike, I want to take a moment to see if Mark, your I'll say co-pilot, has anything to add, because we recognize his contributions too from the Pluto SDR. He helped us with GNU Radio a couple years ago with kind of getting a head start on that. So, Mark, anything from you?
I'll just add to, can you hear me okay?
Yeah, no problem.
Okay, I'll just add to what Mike said about low level signal and having to be amplified. Down at Earth, that signal coming down off the ISS is somewhere in the -70 to -95 dB range. So the receiver would like to see between -40 and -50. So that's why Mike has both the LNA, which Mike will have to give you the dB amplification of that. We have both the LNA and a coax amp to get the signal up to the range where the receiver is happy and can make something of it. And quick thought on the using the Ubiquity hardware that's intended for Wi-Fi, and we're using it for Arden and HMS, HSMM. I think my first thought is that the proprietary driver that Ubiquity provides for us to use is strictly doing Wi-Fi. I don't think we have direct access to the hardware where we could twiddle it to do our DATV instead of Wi-Fi. But that's just a quick thought. I don't have any background to say that's 100% correct. That's just my guess. And Mike deserves all the credit. I was just the guy that he would say, how hard would it be to, umpty ump. Back to Mike.
Yeah, don't let himself short. Mark is the brains. I'm the one who just comes up with stupid ideas, but Mark is the one that understands the software.
Is the dish tuned up well, do you feel, or is that signal strength that you're talking about the calculated available signal, or is that the signal that you're thinking that you're measuring?
As far as we can tell, and this has been our challenge the whole time, it's so hard to test gigahertz stuff without really expensive things. So that's why we built a test transmitter setup, and Mark built this antenna, and we have it mounted on the tower, aimed at our receiver, and we can play with frequencies and all sorts of things. But the software wise, the whole system is pretty tolerant on frequencies. There's quite a wide range that it'll tune into as long as it's there. And so we're not concerned with that part of it. It's just the signal gain is the hard part. But being off frequency a little bit, uh, it's a bit more tolerant than you'd expect. I didn't really mention this, but it's a two. Let me think. I think it's 2.7 uh, megahertz wide signal is what we're playing with, but it's pretty tolerant on reception. We haven't had a problem with that, and with our test transmitter, we tried that. We tried moving different frequencies to see what happens. Mostly so we have a baseline to know if it's going bad, why it's going bad, so we can kind of see the symptoms of it.
Yeah. I can tell you those are all good best practice kinds of things to do.
Again, I appreciate the help of the North Texas Microwave Society of getting us that filter, because we're stuck without it, completely stuck without it.
Very good. You guys don't have to stick around. This is going to get kind of technical into the microwave area, but I did want to tell you that Bob's question, that was from Bob Strickland about the, were you working with, I would call it a link budget of gain over losses, was kind of what I would paraphrase his question as, versus just empirical, or not really just go out and try it and make sure it's strong enough to do the job. Our next speaker, Al Ward, which I know you know him, he's got a demonstration at 47 gigahertz, or he's going to describe an experiment that he did where the test range fits on top of a tabletop. It's such a high frequency, and he's going to explain to us how just knowing some variable information, you can calculate the gain of the horn that were involved, which is the same thing we're talking about here. Is how do we overcome the losses, or how do we come up with empirical data to help us understand the pieces we're dealing with? And then, as you said, when you have a baseline, you have like a dipstick where you can check things over time to be sure they're not degrading, or that's been some kind of unusual improvement that you can't account for. So keep up the good work.
Again, appreciate all the help. I can't stick around for the meeting. I have another thing I got to do, but I appreciate all the help. And if you have any more questions, you can always contact me, and I'll tell Mark to give you an answer.
Well, thank you, Mike, and thank you, Mark. 7-3.
7-3. Thanks a lot.
Thanks for having us.
Al, you are up next. Do you want this platform raised so that you can stand?
Oh.
You're going to sit? Okay, let me cue up your presentation.
The attendees.
Okay, really good. I think I ever started yours.
Good to go?
Rolls or button. All right, for arrows. This is what's going out over the air.
Okay.
It may differ from that.
Okay. All right. Good enough. I'll stand up to do it. Okay. Good afternoon, guys. And thank you, David, for hosting us. I appreciate that. We got room for plenty more, don't we? These experiments that I did were kind of prompted by some questions I had. Number one, loss in front of between a feed horn and a waveguide relay. And number two was to analyze the losses of that little piece of Cowtown there out in front of a horn. So I didn't do any tests at 10 gigahertz, but the results are so good at 24, it's got to be even better down at 10 gig. So it's a two-parter. And like I said, the first part's going to deal with the WR42. I have a problem in my waveguide EME system where bugs and insects are getting inside the feed horn. Well, that's okay, but then they go even further into the waveguide relay. And they really screwed up the works when they did that. It locked things up. And when you're running 100 watt TWT on 24 gigahertz, you always want the transmitter to go out to the feed horn. And you don't even want to warm up a load because it'll probably burn it up. But I was more concerned about the preamp longevity. So these are some of the windows I was looking at. The first two that are shown there are the Andrews windows. And they are very interesting in that I bought these on eBay some time ago. And I can't remember the actual loss back then that I measured, but it's a two-parter thing. They're relatively thick, at least the waveguide is, but the mylar that's in there is rather thin. And I think I measured it at a couple milliamps. But you can see, yeah, here is with it together. You can see the four screws that hold it. And over here is the two pieces. So I was able to measure the thickness of the mylar, and I think it's about 2 mils or so. Then I got this other one, I say unknown manufacturer, and it was just like a piece of mylar kind of sandwiched down or kind of glued or sticky taped to the piece of waveguide. And this other unit here is off of 23 gigahertz system, and that's right here. And I can measure the thickness of it, and I've got it, it's in the table, but it's not very thick, and it's some sort of a mylar or some sort of dielectric material. And actually, that loss wasn't too bad either. And then Al just brought this for show and tell. It's so far as I can tell, it's kind of somewhere between WR75 and WR90. But if you want to come up here and take a look at it, you can see it. So these are show and tells for if you want to come up during the break or something and take a look at them. So now the transverter I used was the Wavelab down converter that Jim supplied a lot of us. And I figured that was a good test bench. My converter for 24 gigahertz is out at the feed and too big to bring in. So I use this, and the noise figure, is about 2.5 dB or so. And this is the actual waveguide assembly. This was sitting out at my dish for about, I think 20 years or so. And I had more than insect problems in there. One winter, a darn squirrel got in there through a big hole that I had on the side. And he made a nice little home, as well as he's made homes everywhere, including the engine section of my Jeep. But it's pretty simple. You've got a waveguide relay. I got the preamp right here. This was done by a DU3T. Ran out of go-go just there. And let's see, how else can I show this? Can't see this. Let me just walk over here. Here's a waveguide to a coax adapter. Goes through an isolator and into an adapter to go from 3.5 millimeter to 2.4 millimeter. And right where I showed this arrow is where I actually added the dielectric materials. As you can see, let's see, folks out there should be able to see that red arrow. I don't know why because that's not going to show up out there. So that's the test bed. And the problem is it was sometimes hard to sandwich everything together at that point, but I tried to do the best I could in measuring the loss. And what I found out, basically the increase in the noise figure is the loss of the dielectric window. And I had to add the isolator because, it's a high ENR noise source. And I guess sometimes some of the results looked a little questionable. And anytime you run a high ENR noise source on an LNA that's low noise and very sensitive to load, you're going to see some variations that most likely aren't real. So the isolator sure helped out in that regard. So these are the losses I measured. And basically, the noise figures started out at 1.7 dB for the LNA and the waveguide relay. And these are additional losses that show up in noise figure. So 1.7 was with no window. 1.75 is with the saran wrap. That's the best. It's about a half a mil thick. Not a very good pressure window. I don't think it'll even handle the pressure out of a vacuum or out of an aquarium pump, but it's the lowest loss material out there, and that's what I'm using right now. But that 2 mil Cowtown, only about 0.06 dB, and I'm sure it can handle more than a pound or two. I've got some over here, Mott's KD5ZX gave to the group, and I've got some envelopes and I got scissors, and if you guys want any Cowtown, feel free, I'll cut it. And I also got some 10 mil Teflon over there as well, if that appeals to anybody. But you can see the pressure window from Andrews is only about 1/10 of a dB. And that may have just been a combination of dielectric loss and then just the additional transmission line, if you will, going to the LNA. But that's pretty low. And then the unknown origin pressure window a little bit more. And then the Cowtown, the 7 mil Cowtown is what we got from Mott's.
What's the purpose of the pressure window? So, new guy here. I don't. What's that?
Well, in a waveguide system, most of the time you're on a pressurized waveguide. You just got to kind of keep it dry, try to keep moisture out. And even, the professionals will evacuate first, then pressurize. I don't do that. I pressurize. And sometimes I noticed, I don't pressurize this particular assembly, but all my waveguide that goes out to the tower and stuff like that, it'll always be pressurized.
See.
As sealed as I can get it, yeah. 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 I'm not religious about baking it out as much as I was years ago. But here's some 7 mil Cowtown that we got from Mott's. And like I say, there's some 2 mil over there, if that's of any interest to anybody. Oh, and Kent Britton had an idea, well, what about a mica insulator? So I go home and I had some TO220, I guess, mica insulators. It really wasn't that bad at 24 gigahertz, 0.2 dB, or 0.2 dB. And this guy here turned out to be 1/4 of a dB, which I guess isn't too bad. And of course, they're not too concerned about noise figure, but for me, I don't want to see the noise figure go up even 1/10 of a dB, because 1/10 of a dB when you're looking out at the sky is more than 1/10 of a dB of sensitivity loss. So it's very important for me there at 24 and 47. Any questions on that we didn't talk about? Yes, sir.
Yeah, some of these critters have pretty sharp teeth and claws. They have good carpentry skills. Is that going to be mechanically resistant to that type of attack?
No, I don't think so. I'm going to try it. Yeah, but that 2 mil Cowtown is probably the second best thing to try. All right. Well, the next thing that came up was, what about dielectric loss at 47 gigahertz? And so I decided to set up my test range that you can see over here. anyway, the power goes in on the left side and comes out on the right side. And what we need to do when we're going to measure antenna gain, of course, that wasn't the original goal. I just wanted to put dielectric in front of the feed horn and see what the loss was, because that's exactly what Jim's doing here. He's got the horn on the inside. He's got the dielectric here and a dielectric window. By the way, this is really nice. Yeah, you did a nice job. Thank you.
Yeah, it's got the two.
Okay. Yeah. So what I thought I would do is we'll talk about a little bit about equations, because this is kind of an interesting study, and it's not real involved. And some of you might learn something that you didn't know before. But what we have to do is we need to operate in the far field. If you're coming in too close, all the rays, if you will, are not all in phase, and you don't have a plane wave. So we need it to be far enough apart such that we have a plane wave generated. So that's 2D squared over wavelength is the minimum distance. And it's a pretty simple equation, because D, the diameter, and wavelength just have to be in the same units. Of course, we're talking about high frequency here and small things, so inches is the appropriate way to treat things. Now, the diameter is 1.375 inches, and the wavelength is a 1/4 inch at 47 gigahertz. So it's not very big. And it turns out the minimum is 15 and 1/8 inches. Well, this platform is 35.5 in between. So I feel like it probably meets the 2D squared over lambda. But this is the platform just kind of set up at my home. And I had to do it kind of near the bench, because all the equipment is right there on the bench. So I'm using an HP 8340 signal generator pointed to there. And it comes in about, 15.696.033. That's so I can get as close as I can to 47088.1. Actually, it's 0.099. But it gets amplified and then runs through a multiplier. And I took it through an isolator as well, because I figure I'll be disrupting the field a little bit when I add the material in front of it. So I put that on the transmit side, if you will. So we're transmitting on the left, and we're receiving on the right side. And, it's a power sensor, an HP 8487A, and using an HP power meter. Well, I didn't point that out, but it's the one with the green display up there. Can't remember the number on that.
I think the full looks like control key, and let's flip them out and turn the laser pointer on.
On the laptop?
Yeah.
Not sure what you're saying.
Control left stick. Okay. What with laser pointer is not a real laser, right? No, it turns the mouse pointer into a laser.
Okay. Control, click. Okay. Oh. But if I let go, does it go away?
Yeah.
Oh, yeah. So that requires a lot of coordination.
Sure does.
And as you can see, I lost the signal. There.
All right.
Yeah, you got to press that and that.
Yeah. Let me see.
Okay. You can send with your left hand.
Yeah.
Your toes and finger. Okay.
Okay. Thank you. So this is the test platform. It was set up just out on the bench, out in front of the bench. And like I said, it couldn't be too far away from the equipment, because that's what's needed to make the test. So I thought, well, I'll run these tests and we'll see what the results are and see if we believe them or not. So the first thing I did was, well, let's see how much signal we have. And it turns out I had about -2 dBm at 47 gigahertz coming out of the isolator. And the received signal is about -24 dBm. Now, this is after being amplified by the horn. So it's about 20 dB over the noise on the 4419 power meter, which is more than enough, to make measurements. So all I did was, while looking at the power meter, very careful, try not to get in the field, would insert this in front of the feed horn and look at the additional loss. And I did have to redo it a couple of times because here I am getting pretty close, within the arm's length, obviously. But I think I still got some pretty good measurements out of it. And again, the saran wrap wins. Really very hard to measure that loss, 0.05 dB. And the 2 mil Kapton was also real close, just like it was on 24 gigahertz. So it's a second choice, a good choice. Then I had some old Teflon sitting around. It's 10 mil Teflon. That loss is 0.12 dB, still not too bad. And then by mistake, when I was out in the shop, I thought I had some clear mylar or polyethylene, but it turned out to be painter's cloth. And I thought, well, what the hell? So I looked at that, and it was about 0.14 dB. Now, the 7 mil Kapton is getting a little bit lossier up there. It's like 0.27 dB. And let's see, I wrote down mylar. Oh, okay, that was another film that I have. I had no idea what it was, but it measured out at 0.4 dB. Then I thought, well, let's do something crazy. I store my stuff in these Sterilite 6-quart containers. So I thought, what if you stick a beacon in there? How much loss would there be? So I measured 0.62 dB at 47 gigahertz on it. Not the end of the world, but I don't really want to blow away too much loss, but I just had to do that. So all the materials turned out to be pretty good. And I've used saran wrap before at 47 gigahertz where I've just taped it around the feed horn right at the end of it. It's not exposed really. It's not exposed to the elements per se when I'm not using it, and it doesn't look up at the sun. So it lasted for a pretty long time. All right, well, then the next thing is, I thought since I've got 2 horns that are in the far field, when I measure the gain of the horn. I've done this before years ago and actually put it in a central states proceedings. Here's the proceedings. This dates back to 1986, which is before the ARRL took over publishing the proceedings. Yeah. We used to put all these together ourselves, didn't we? Yeah. Well, here's my paper. September 16th, 1985. Was that over 40 years ago? And I measured the gain of a 3-pound coffee can at 1296. Now, back then, 3-pound coffee cans, I made a great feed and also a great reference antenna. I used to have one up on the tower, and I could switch between them. And I drug that thing out, and man, it's so darn rusted, and it's got holes in it. And so I thought, I'll just leave that at home. But so I thought, well, why not try it here? I had no idea what Paul thinks the gain of the horns are. And in fact, I finally just got a response from him yesterday. He'd been out of the country. So here's the test method. We know we had minus 2 dBm going in. We got minus 24 dBm going out. So what happens between the 2 horns? Well, we have horn gain, we have path loss, and have another horn gain. So when you add them all up, of course, you're going to consider path loss is actually 4 pi d over lambda squared. So at 47 gigahertz, there's 65 dB of loss over 30 some odd inches. Really quite a bit when you think about it. But if you go through all the calculations, and if you believe my numbers, I think a horn is about 21.3 dBi, one of the horns. So I asked Paul what he thought it was. Well, let me back up. If you look at the gain or the directivity, that's 4 pi a over lambda squared. That's a 100% efficiency number, so it's really gain, and they call it directivity. But no antenna is 100% perfect. Horns probably are pretty good, but most dishes are probably 50, 55%, maybe 60 if you're lucky. Offset fed dishes, maybe a little bit higher, 75%. So when I got the message back from Paul, and he said he simulated 22 dBi. And I told him, well, I measured 21.3, so maybe that's not too bad. And but it could be low. I mean, it's in my shop. Got ground reflections. I'm in there doing stuff. Test equipment variations. I do get those. I mean, we're talking about 47 gigahertz. I really need to put a heat sink on this guy, because this guy is warming up. And also, we put a 12 volt, 5 volt regulator in there. It's lucky it's not blown up. But I still thought the numbers were actually pretty good. All right, then something else I wanted to throw out there at you. Do you have a question, David? Okay. This number, 2.9507148. That's my little cheat sheet number. Because, if I'm trying to figure out wavelength, I don't want to, figure out or take free space, and then divide, it's just too big of numbers. I want something simple. So the simple number is 2.59507.148. You can divide that by any frequency in gigahertz, and you get a quarter wavelength. And of course, you can even use it for a 160 meter antenna, but you'll get a lot of inches, But that's what I use. And it turns out I have remembered another number from way back when. I did this when I first started to work at TI back in 73, I guess. Needed a shortcut. And I had in my brain 2.95071353. Been remembering that for 40 some odd years. Then I went through the calculation. I thought, well, if I'm going to tell people about that number, I better calculate it. So I calculated, and I got a different number. And I thought, that's a speed of light. Has it been constant, or maybe that was like an SR10 calculator, the TI back then. I think they came out. What's that? That. Which you see a lot of times, roughly 3 times 10 to the eighth. Yeah, around it, I guess. Yeah. Unfortunately, this is going the wrong way. I mean, I couldn't defend my 2.9507135. So now I got to remember something else for the next 40 years. But that's okay. But it's just a shortcut, and it turns out it made very little difference at 47 gigahertz in a quarter wavelength. It was still 0.25 something or other. So that's a little shortcut, 2.9507148, and I guess that's pretty close. And here's
most of us can't measure. Most of us don't measure what's going to measure them. 3 decimal places.
Yeah. Well, it's how many significant digits do you have in your calculator? I even tried it on my laptop, and I did get this number again. But on my little solar operated TI calculator, no, I didn't have enough places. But anyway, just a tidbit of information. Maybe useless to you, but it made it a lot easier for me. So anyway, that's how I calculate it. All right, so I mentioned before, I don't pressurize my EME system on 24 gigahertz. It's all out at the feed, and including the TWT, but this is mainly just to keep insects out. So that's why I'm going to use the Saran wrap. And I've used it also on 47. And like I mentioned, that 2 mil Cowtown, which we have quite a bit of here, we can cut off some sections. I've got an envelope. You probably won't need a lot of it unless you're going to build a big window, but that's some pretty nice stuff. And that was courtesy of Mott's KD5FZX. So anyway, the goal was to basically measure some losses, and I did that, and also present a couple other subjects to you. All right, that's all I had. Any questions on that part? All right.
Back over here. Okay.
Take a walk around the park first.
Yeah, can we take a 5-minute break? Just 5 minutes. Take a picture.
Did you? Okay.
One.
Thanks. Thank President.
Thank you. I think I'm gonna do like,
1 minute, she said.
yeah, I'm gonna do like, just stand up and project to the crowd and.
And you want that to come up?
Yeah. Yeah, it's pretty easy to see.
Okay, let me get this. Tuned up.
Then the TV very well.
Yeah, I was having trouble seeing that.
Yeah, me too. Well, compared to those last two presentations, I feel like, well, I got a real president. So
Everybody's interested in all this.
here we go. Oh, wait, they look at that.
I think it's that way, being reflected, then it's.
You can arrow, you can roll, and then if you're really coordinated, you can do the control left click. This is what's going out over there.
Well, there's a.
Move it real slow. Come, yeah, just right there. Okay.
It's here on the.
I'll investigate that because it's probably a setting.
Yeah, over the 2 of 2-4, and I don't. Well, I see it here though. It's jerky. You see it. You do see it.
So that's what's going on because this is an attendee.
Okay, cool.
So if you can see it here, you can see it out there. That's my video. Apparently it doesn't count in the video.
Readers.
Bathroom's empty. Vacancy.
So, will affect the gaming experience. That's why we don't like see it's a. Remember, well, it's not fun. Yeah, I guess, but like when Conway or if I use for weather, I.e. invaders. I was generally doing see on moments. It's sort of like elevate for that lights flag. We had to build this thing. So that helps me a lot. Preamps are very sensitive. You get to see finely tuned the laser, right? Were you turn on the yeah, I mean, it's before. It's fine. I'm sorry. Number 10. Yes,
Well, the idea was for the 1024, but I was using that same. It's one of the around Waveguide and Wavelab. Yeah, I can only very thin because if you pull this way, it's very yes, your crane shirts and going to get. I should have brought them more. Yep. I mean, I could easily start looking at a point forward, so it's like nothing. Yeah, because I mean, I was like, it's just this is how less is reflected. Should I be using that as a for the cover?
You might want to write in that PowerPoint and select laser, it will permanently stay on. That way the people in the meeting can see what just right click on the mouse button and select laser pointer. Yeah.
Let's see.
So
Pointer
right click in the
options.
window. Yeah, just right click in the presenter.
Laser pointer right there.
Yeah, turn that on. There you go.
Oh,
Now
look
it's
at
play
that.
on. That way people can see. Yeah, people can see what you're pointing at.
For that.
What'd you do? You can presentation.
That's right.
Thank you. Okay, ready? I guess I'll get you.
All right, everybody, we're going to start again. And at this point, we're going to have Keith Berglund talk to us about his adventure in the Wavelab 24 gig transverter and all of its associating supporting pieces as he has converted it from being ground-based to being on the tower. So, Keith, go right ahead.
Yeah, but I see it. Yes. We've got the laser. We're ready to go?
Yes.
All right. A few months ago, Jim KM5PO gifted to me one of these Wavelab 24 gig transverters. And he even programmed it for my particular IF at 432, and we'll get into that. Anyway, here's my history on 24 gig. Jim gave me that tripod mounted unit, and thank you, Jim. It was very useful. And I made several cues from the backyard, many of which is in this room right now. And but my very, very first QSO was with W5LUA. Surprised, because I have homebrew transverters for 902, 1296, 2304, 3456, and 10 gig, and he was my first Q on every single one of them. So because we're only about 10 miles apart. Anyway, but the range I found was quite limited due to houses and trees and anything else that gets in the way. And as we all know at microwave, the higher you are, the better. If you're on a mountaintop or a hilltop or something like that, that's better. Or if you're on flatlands, being on a tower is pretty okay. So what I decided to do, and the purpose of this presentation, is how I took a ground-mounted unit, busted up all the pieces, recombined them to have some on the tower and some in the shack. So this is the guts of the Wavelab. On the left-hand side over here, you see the actual transverter. Now, how this works, I'm not going to go into today because Jim over there has produced several learned papers on how the guts of this thing work inside, and that's not the point of this presentation. Off on the right is a control board that some Dutch guy, PA0, whatever, that glues on the top of the silver portion and makes the transverter. The top is the control board, the lower area is just the transverter itself. You can see on the left and right, there's some SMA connectors sitting out, one for transmit, one for receive. So my job was to take that, repackage it, do a little bit of link budget, that sort of thing. Anyway, here's the basic block diagram of the whole project. Simplified. I guess the best place to start is in the upper right hand, push to talk switch, either manual or from a rig, but the push to talk. And that goes into a sequencer, which its first duty is to take that latching relay driver and drive the relay from receive to transmit. And then it says it gives permission on the PTT line for the transmitter to say, okay, now I can start transmitting. There's a few milliseconds delay. We don't know what a sequencer is. Anyway, IF is 432, 10 megahertz reference. The more accurate, the better. And the thing runs off, wants to run off 7.1 volts, not 12. So there's a little DC to DC converter in the box as well. And as a small side note, there's a voltage meter out there because there's a place on that transverter board that if you tap off on the right little pin, there's a little directional coupler inside of it that'll produce a negative voltage as a function of RF power. Now, it's not calibrated at all, but it just really gives you a good feeling when you're hitting that Morse code key and you see that needle going ba 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 ba. Oh, you say, oh look, I'm putting out power. I feel good. Anyway, so any questions on the block diagram? All right. So this is the backside of one of those radio wave antennas.
Real question.
Yes, sir.
What's the not really what's the dollar? $1,000 thing, 4,000.
I don't know, Jim. He bought them on eBay. No, the radio is mine. I bought that.
Yeah,
So.
Well, the other stuff,
Well, it's cheap.
stuff there, David, probably about 250.
Yeah. The relay driver was about $30, and the sequencer was about $30, and $30 here and $30 there, and soon you're talking real money. All right, cool. Anyway, this is the back of the radio waves antenna. You're actually seeing the backside of it, and that area with the blue tape on it is the waveguide sticking out of the back of the antenna. And the antenna itself in this picture is this white area. It's actually facing down into the table. But the thing to note is the metal plate all around that waveguide. And it was formerly meant in its first life to where all the mounting gear would mount to a big old pole. Well, we're not going to do that this way, but we're going to use that area. So this is how it was used. I mean, that's the same antenna you saw previously. That is that, with all the goop attached to it. So from top to bottom, you've got the sequencer here. You got the relay latching driver. The green board here, of course, is the Wavelab module. You got the TR relay, 10 megahertz source, voltage regulator, and manual TR switch. So it just took all this stuff, mounted it to the back of that plate. And then what you get to do is mount it on a plate, mount it on a tripod, and go to town. Now, this is when Jim and I first went out to test my module that he had aligned for me. And we set up in the parking lot of a church at Echo Mike 12 IL. And so I said, guess, all you guys are learning, guess which antenna here has more gain? Okay. Yeah, pause for laughter. So here I am in my backyard portable. And I made contacts with, a couple of other guys in this room, AA5C and AA5AM from this location, and of course Al. But one of the comedy things is one of my buddies noticed in the picture, you notice what I have my IC 9700 propped up on. I'm sitting out in the backyard and I want the radio to have more angle to it. Best thing I had was my $200 and some odd Fluke 87 meter. So you see the little yellow area down there. It is very hot that day. All right. So here's what we're going to do with that tripod you just saw in the backyard. We're going to bust it up and put some of it up on the tower and some of it in the shack. So basic block diagram. You're going to have all the components that's necessary to go into the tower box. Of course, the antenna. Then from a piece of like rotor cable, it's really rotor cable, into the shack box. 9700 makes 432 megahertz. 50 foot of RG213. You say, well, isn't that lossy? I have to turn the 9700 down to like 1 watt or so to drive this. The 9700 can put out like 75 watts. I'm turning it all down to practically zero. And so 2 or 3 dB of RJ213 is not going to kill me. So anyway, the rotor cable and rotor. I chose this Yaesu rotor because A, it's the cheapest one I could find. And the other one is there's no break in it. You know the high gain rotors that have the big old clunk clunk break? Well, those teeth in the high gain rotors have several angles to them. Like I think on the tail twister, it's 5 degrees. And so on a tri-bander, you'd never see the difference 5 degrees. But on this antenna, 5 degrees would make the difference between making the Q and not. Because if it's just so that laser sharp. And so, I needed something that was just gear driven that I could do fine adjustments between angles. Anyway, come on. Oh, well, let's go that way. All right. So what does the tower box looks like? Well, it's a weatherproof sort of a NEMA enclosure. And I found it on eBay for about $30. and I obtained some aluminum plate here that's 3/16. And the idea is to take this plate and put it in that box and mount all the pieces to it, much like you saw on the back of the tripod. So anyway, I drills a hole in the back of the box. Remember, that's the back of the waveguide and the Wavelab antenna. And notice then I drill all the holes here to match up with these holes in here. These are threaded 1/4 holes. And so I needed 8 bolts, about inch and a half, and it goes through that metal plate, through the box, through into the backside of the antenna here, and it really holds it very firmly to the backside of the antenna. So anyway, now it's time, now that I got that nice plate done, pull it back out of the box and start mounting the goop to it. And it's surprisingly how much it is similar to what was on the tripod, except with a few changes. To get the power and control to it, I put in a barrier terminal strip, and then just started, here's a switch, but it's not mounted to anything just yet. But anyway, when you get all the parts together and in the tower box, that's what it looks like. Very similar to the tripod. Here's 10 megahertz up here, sequencer, latching relay, module, transverter, and then a power strip that has 12-volt DC ground, and then 4 other major lines. Push to talk. Let's see, that meter voltage. And then I attached some wires to certain parts of the Wavelab board that would give me an indication of phase lock and TX. Let me just go to the next one here. This is with the power turned on. When the module is, the transverter is powered, LEDs come on all over this board. And when you hit transmit, a transmit LED comes on. And when it's phase lock, a phase lock comes on. And also, I needed that voltage up here to come over. That gives me the negative voltage as a function of RF power. So anyway, any questions so far?
Why elect?
That's what he gave me. Yeah. Thanks.
We had a couple other questions, if you don't mind.
Yeah. What we're here
Is
for.
the outdoor box metal?
No.
Plastic?
Yes. It is FEMA, something or other rated. If you turn it at the right angle, it meets certain weatherproof conditions. And they advertise this box as weatherproof.
Okay. Are you using a gland for the cable exits? i.e. rubber that crushes?
No, okay. I had that sort of in the presentation, but I deleted it because I thought it was just redundant information of how it's a amp connector that is a 1/4 twist black, and it has rubber in it. So then even after that, even when it's on the tower, I slide the heat shrink up, shrink it down, and tie wrap it just to be sure.
Okay. One last question. How did you transfer the hole patterns from the original back of that dish plate to your nice square 3/16 plate?
That was another couple of slides I cut because I thought it was just too much information for one presentation. But to answer your question, I cut out a piece of paper, put a 1 3/4 inch holes in it, laid it on the back of the antenna, and just took my thumb and started pressing where the depressions were. And the dirtier your fingers, the better, because it makes a nice little hole. And so anyway, taped that up to the back of the plastic box and just match drilled that. And it worked fine. I should have maybe included that slide.
I trust you. You can trust me. I'll go over that. Take that a little plate off.
No, you can't. I attempted one time and it was just impossible.
That's all.
One engineer to the next. That's right.
Okay, now that we got the tower box squared away, it's now time to go into the shack box. That is, I call it the shack box. It's just a control, and it gets the DC voltages and all the commands, and the LEDs come on right. And so it has to have a power supply, on and off switches and fuses, lock LED, TX LED. Come on, I didn't say do it. TX LED, 5-volt LED. And as we all know, the more LEDs you have on a project, the more grandiose it is. Yes. Okay, well, I'll get into that here. That's a good question. Actually, I put a buffer between the board and the LEDs. So anyway, it's opto-isolating. Anyway, then the DC ammeter, then the, come on, this is, then of course, in the shack, a push-to-talk switch of some sort, just a toggle switch. Anyway, this is a schematic of in the shack box, and it looks way more complicated than it really is. When you actually put this stuff in the box, you go, is that all there is? But what we have here is the 12 volts comes in from the left side on a Anderson connector, fuse, push-to-talk switch, ammeter, and then to the bus for 12-volt distribution to up the tower and everybody else that needs it in the box. The push-to-talk switch, of course, is just bringing that PTT line to ground. Power meter, and then here's what you're talking about. This is an LED driver. I was afraid, I didn't know how much that the circuit board could drive in terms of current to the LED. So I soldered on a 100 ohm resistor, put some heat shrink on it, brought it down, and then to a high input impedance buffer. It's a open collector, opto-isolated little 8-pin chip that I just had. And so it's a voltage controls the current for the LEDs to come on. Works really nice. Right. So this is MacDoodling. Even before, when you don't even have anything, the hardware just yet, you're just imagining in your mind. And you take, and I call it paper dolls. You take and move this switch over to here, and that switch over to there, and go, no, that doesn't look right. And so you finally come up with a configuration that you think, oh, that's going to serve the purpose. So that was the initial thought, and that's how it turned out. But you see, they're the same thing, sort of. But all the switches, RF voltmeter, DC ammeter, and of course a whole host of LEDs. You got to have that.
Did you run?
Yes. Well, I happen to have this. This is a 2U project box that I've had for like 10 years. It says I'm not getting any younger. I might as well just use what I have. And it worked out nicely. A little too big, but as I say up in the comments that are kind of blocked out by and it says I could have used a smaller box, but it's what I had, and use what you got. So in the upper left-hand corner, you got I've lost my laser pointer here. On the upper left-hand corner, you have where the Anderson connector is. Fuse goes down to the power switch. Come on. Ammeter, and that's that circuit board with the opto isolator I was talking to you about. Could I have made that smaller? Yeah, but I had it. It was in the box. I just put the parts on it. I wasn't caring about size or form or fit or function here. Hey, I didn't know it could do that. 5-volt to 12-volt to 5-volt converter for the LEDs and to drive that switch. Cool. So anyway, now that we have a good complete shack box and a good complete tower box, now we have to worry about how to get this thing up on the tower. Okay. So what I was going to do is I have a 50-foot Roam 25. I also have 80-foot of Roam 45, but I just wanted to put it a little closer to the shack. And I wanted it about 40 foot up. And I have to make some brackets to hold all this stuff. And it's got to support the antenna about 2 foot away from the tower to let it rotate around. It's got to be able to rotate 360. It must support the weight of the tower box and the rotor. This whole thing is not really that heavy. 10 pounds or... Now, that's with the rotor. And then I got to use the existing base of the radio antenna. And that's not optimum, as I say. It's just, that's a scratch your head to figure out how to mount that. So anyway, take a note. This is the old tripod unit. This L foot down there at the bottom there. And that's what kind of holds the whole antenna up. And so that's really the only thing I had to be able to attach to. So this is the bottom on the left side, the bottom of that L bracket. And so I took a piece of angle aluminum and drilled 2 holes. You see the bolt holes there and there. And it corresponds to the bolt holes there and there. They line up, and I just threaded them up and now put a couple of those DX Engineering saddle U-bolts on there, which holds everything really good. I'll never put another antenna up that doesn't have those aluminum saddles on it. It just holds nicely. So anyway, that's what it looks like when you get it all put together. Here's the rotor on the bottom, the radio waves antenna glued to the tower box, and then you have the 2 lines that come down as the RG213 and the rotor control and power cable. Okay. So anyway, this is a bracket that I made to hold it away from the tower. Now, Jim actually said, "What CAD program did you use on that?" I says, "I just took PowerPoint and I took 2 engineering design and graphics courses in 1976, so I guess I still remember some of this, So anyway, what I wanted to do is be able to take those saddle brackets and put them on the Roan 25 tower, and this is the bolt hole pattern that would fit each side of a Roan 25. And to make sure that my drawing was correct, I actually put a piece of paper on the table, drew all this stuff out by hand, then walked the paper out to the Roan 25 and held it up there. Yep, that lines up. So then I had a warm feeling that I could drill on this $75 piece of aluminum. A metal is expensive nowadays. So anyway, this is a 4x4 by 36-inch long and like 1/4 inch thick. It's robust, okay? And so when you get it all up on the tower, that's what you got.
It's not on the same tower.
No, this is on the other tower. Well, you can obviously see what you got. You got the bracket, the rotor, the black rotor, the antenna box, and the tower box. And it wasn't really hard to get up compared to a tri-band or something because it's just hand over hand. You didn't even need a gym pole. So anyway, on this antenna?
Oh, I thought you were talking about the tower.
Oh, no. Just to mount this antenna on the tower. Yeah, it's just 10 or 15 pounds. You can just tie it on there and hand over hand. And
you doesn't put up Roan 45 without a gym pole.
Okay. Boy, my hat's off to him. Okay, anyway, you can see this is about at the same level as my ham floor rotor, which is at about the 40-foot level. Anyway, come on. Anyway, it works. Yay. I now have three whole grids on 24. L over here on 13, Jim in 12 and 23. And I've worked a couple of other guys in this room too that are on 24 gig. Maybe now that the things up on the tower will rework again and you see how much louder I am, hopefully. So anyway, other than that, that was what I did.
Any question?
Yeah, it's not as complicated as what Al did with all the waveguide stuff, but it was a mechanical project, not an electrical one. Okay, that's all I got.
Questions for Keith?
If you can push the talk between the Wavelab unit 9700.
Me, click, toggle switch. Okay, and this is a procedure I have to do to make sure I'm not transmitting into it. I stick my left hand in my pocket. I click the on, and then I can see the TX LED come on. Maybe a 1/4 of a second later, and then I can reach down to the key and start going.
So your sequences. So it does some of that because it doesn't make the 9700 go and transmit.
No, 9700 is just a separate radio in the shack. I'm the push to talk. And then that goes up to the push to talk line. Now the sequencer up in the tower box does its sequencer thing with the latching relay and the coaxial relay.
You have to put your
After the TX light comes on, yes. It's not synced. It's just me. Yeah, because I don't want to be transmitting with one hand while clicking it on before it was ready. No. But my key is on the right hand side. Okay. That's well, okay. Hope to talk to half of you in this room again.
Yeah. Down to one. Well, yeah,
I'll give you back another one here.
so that was another $100. We're talking about the cost. So it is a great buy because it's a great dish, 12-inch dish with a reflector that looks like a mirror.
No, it's trivial, but they have a weep hole in that radome. And now that I'm mounting it this way, I did undo those screws, rotated the radome 90 degrees, and screwed them back up so that the weep hole would be pointing downwards. And you're right, that's a mirror in there. You can see yourself. Well, if they can get into a hole that big. Okay. Thanks you for listening.
Yeah.
You're asking about 24 gig equipment. I mean, you're familiar with Tony Electronics. You know, they make some very nice equipment. And they have trained burgers for both the 24 and 47 and 10. And it's unusual for them to have the 47, but they're still making it. I guess they the part is still being made. But they do sell, I think, a 3-watt 24 gig. And they're
Out of Germany?
yeah, Tony Electronics.
Maybe I'll wait for the next time guys to get you sort of.
Well, they're supposed to, aren't they?
They're supposed to. They showed it off, but they won't take my MF yet. So
What was it, David? Control left click. Oh,
yes.
okay. I guess if you touch the screen, you're going to lose that. I've got it now, but he touched it. I think he was touching the screen. Keith was when it went away. He lost his pointer. Okay, so we'll move on to this, and I'm going to try to speed up just a little bit from, and for the sake of time, because the next presentation is a little bit on the long side. I probably have to cut it down too. And I also want to, are you still broadcasting, Bob? I also want to make the blinky lights turn on because this has got the max LEDs you've ever seen. And this is the tri-band beacon, possibility of placing this up at the women's dormitory, or possibly, I mean, could even be over at Bob's Ranch. But the 10, 24, and 47, it's all turned on by using your cell phone. You have to have the secret code, which we'll give to Al. And then you can optionally turn on whichever beacon you want and turn them off as you want. Anyway, I'll turn that on and power it up and let you see the blinky lights here in a moment. But I want to talk to you about these 10 megahertz filters because Mott's, you've heard his name a few times today, KD5ZX. He was inspired from another situation where he wanted to buy some crystals, match them up best he could, and build series crystal filters. And I got some of these. He called me up and he said, "Hey, I got some of these filters. You need to come over and get them." So I went over and got them, and I already had some Amazon purchased 10 megahertz filters, which I thought were probably going to do every bit of the work that it needed to be done. And what reason I got that was because I heard from the Wavelab community, that people were employing these filters after their cheap 10 megahertz OCXO. And of course, we were also building a lot of Wavelab rigs with that same OCXO, and there's many been deployed without these filters. And as we know, the Wavelab's pretty notorious for having some unwanted artifacts. Anyway, on the left side here, you see the MOTS filters and his recorded insertion loss for each of them. And then on the right side, you'll see the Amazon filter. I think Mott's said he bought 100 crystals, and he was able to match up the majority. There were quite a number that were either defective or too far out, but and then he went about assembling them. And so here's a close-up of the work. Mott's work is at the bottom there. He built these on WA5 VJB universal filter boards. Looks like FR4 there. And then the Amazon filter is on the top picture by Bravo Golf 7 Tango Bravo Lima. Classic capacitive coupled LC filter. And then so I put this, it says similar measurements because I actually got what I consider more precise measurements from a nano VNA. It just means I calibrated it better probably, or I bumped a cable on this. But anyway, the two filters, the one on the left is a very broad, slow roll-off wide filter. It's actually 5 megahertz wide to the 10 dB down point on each side of 10. So start at 5, end at 15, the center being 10, you're 10 down on the extreme edges, and then that plot to the left is in 20 megahertz of spectrum. The plot on the right is in 4 kilohertz of spectrum. So as is common, the crystal filter is extremely narrow, but has some insertion loss and probably some impedance issues. And then going on here, here's the nano VNA measurements, which I consider to be a little better. You can see this is 20 megahertz of spectrum, and we're down a roughly 10 on each side, 5 megahertz on each side of center. So it's letting a lot of stuff through. If you're talking about a 10 megahertz filter and it's 10 megahertz wide. But some of the Wavelab guys report this really cleaned up their signal, so I'm not sure. But anyway, the return loss is it's pretty well matched there at 20 down at the center frequency. And here's the MOTS filter on the nano VNA. It is showing about 4 dB insertion loss. MOTS measured 3.7, I think it was, on this particular filter. So again, my cal might not be quite right, or might have bumped a cable. I mean, I get interrupted every 5 minutes, no kidding. And, when I'm at home, working from home, which is Monday and Fridays, they're bugging me to death. And I'm have to leave this on for 2 hours and go over there and deal with something and come back and then come back and forth. So it's not the best of measurement environments. Here's the OCXO. Many of you recognize this. Bob actually 3D printed a case that this fits right into, and it's on your tower and on your rig. I've got a handful of these still. Steve was using one before we repackaged his 10 gigahertz. He's still using this OCXO, but he was using one of Bob's 3D printed cases that this fits so snugly and nicely into. By the way, bragging on Steve, somehow his OCXO is dead nuts on, and he's calibrated it to Al. So, I mean, it don't get better than Al. So, yeah, I know you've got similar. So anyhow, one last pass through this before we jump forward. Here's the spectrum with and without an Amazon filter. So the left side is the spectrum from I'm probably not going to be able to read it, but it's probably 10 kilohertz. Okay. And so you can see some bumps and artifacts here. The Amazon filter doesn't do much. Of course, how could it at 10? Oh, I have it in the heading, 10 kilohertz. So it couldn't possibly help much there. But you'll see in this next picture, the MOTS filter is definitely, you can see the drop down just a hair, so there is a little insertion loss up here, but it is flattened this out better than the insertion loss value of 5 dB. And then here's in 50 kilohertz. So we got some junk here out here about 10 kilohertz away. It probably wasn't in the previous view. And then, Amazon filter's not doing anything as you couldn't expect it to, again, with 5 megahertz bandwidth to 10 dB down point. And then Mott's filter has cleaned it up a little bit. Again, I just say it's cleaned it up better than the insertion loss has affected it. At 200 kilohertz, gets harder to see and pick this apart because now we're getting away from the fundamental, but there's some kind of hash going on here with the Amazon filter to the right side. I really don't understand that unless that's some kind of reflected noise. Because that unit, that unit had the best S21, so I'm not sure where that's coming from. But I looked at it for about a minute and in constant sweep mode, and it stayed right there. That grass growing over to the right side. And then we put it comparison to Motz's filter, and it's nice and flat right down at the noise floor. So,
See, with the bin lab that prompted them.
they saw, first of all, the LO leakage, which is way away. It's not really that close, but I guess we could compute the multiplication factor that could be causing the LO to appear higher than it normally does, because it's got an LO leakage, no doubt, but that would be a gigahertz away.
Yeah.
And then if it's got artifacts that have suddenly appeared up closer to the fundamental, those might be coming from multiplication issues from spurs going through from the 10 meg rev. If they're far enough away, I don't know. I don't think this is done. I just got real interested in another project, so I kind of shortcutted this one and didn't really go to all the extent that I should. And I want to go back to Motz's place because Mott's had a clearer representation of the 24 gig signal. One of which I'm going to try to show here, but it doesn't really show. Here's my measurement for 24 gig, and I'm using an external harmonic mixer on the right side. There's the Wavelab, and there's the OCXO right under the laser pointer gadget right here. Or I guess it's a red dot on the case. And then I'm going to just insert the filters right here in line with this SMA cable. And this is all I have to show here. Mott's had a better way to demo this because I think he was able to zoom in. I had trouble with that external mixer in that when I would try to move the center frequency to get it more in the center of my display, it would jump all the way from the left side to the right side. And then when I would try to move it back, just barely touch it, it would move all the way from the right side back to the left side. So I could never get it in the center where I could then decrease the span and get in close with it. So I want to go back to Mott's and get a better picture here. What he was demoing to me was that cleaning up the 10 megahertz OCXO was giving him better than 3 dB more signal. Well, here it looks like it's a little bit higher, but it's not, I don't think 3 dB. It looks more like 1 or 2. And then this again is kind of hard to tell, but these trees here are dense. I'd like to see into that a little better, whereas this has got a sliver going up in the middle there and not quite as dense. It's also down lower on this valley right here, which is about 6/10 of a division away. And it's trying to happen here too. But anyway, to be followed up, I'll come back with some better spectrum analysis and try to show better how the Mott's filter is the answer. It's the ultimate answer for dealing with this. It will have to have more insertion loss because it's got some impedance issues. They will probably have to have matching network before it would tweak out, just be.
Also put an MSA 04 on the output or something.
Yeah.
Still got any work around.
Or 1 dB attenuators.
Yeah.
Or even gang these guys together.
I was wondering if that would help clean up, say, my 10 gig signal. The spurs. I think they're down 35 dB or so is about it. That's out of the Demi unit with a Digio. Yeah. Oh, who knows up. So
is that where's the reference on that? Is it internal?
No, it comes from the spec review.
No.
Through a couple of distribution amps, and sometimes I wonder too many distribution amps, even though they got filtering, that's still a lot of gain, noise also, you know.
Yeah. I had run into that and I didn't document it. But the distribution amps. The distribution amps is a point where there can be problems, brought in. Okay, so any questions on that?
He had some part numbers, didn't he?
Mott's Crystal?
Yeah.
I don't have them. Yeah, that or I can get them when I pay him a visit. All right, I'm going to jump into the last presentation here, which is something kind of exciting to me and fresh on the mind. Okay. This will definitely be 2 or 3 part set of presentations. There's so do the right click.
You wouldn't know this citing to him, except that he talked about this all the way from Burleson to here.
Which track?
Yeah. It's pretty neat stuff, and I hope that it carries a lot of momentum going forward for several years. So this is about analyzing and forecasting millimeter wave propagation, and lower frequencies, as it turns out, are also going to be useful for this purpose. So we're going to start off with this question, because we have had some success at 47 gigahertz that we don't understand. We have some guesses, but we don't understand. So the question is, what mechanism in the atmosphere enables long over the horizon contacts at 47 gigahertz? These are not line of sight paths. So we confirmed a number of closer in contacts. We thought we were doing great when we made 47 kilometers at 47 gigahertz, but it was soon that record would fall. And so we ended up with 59. We thought that's got to be the best we're ever going to do. And it's like double over the horizon. We have lost the horizon. But then we got 99 kilometers. I mean, what was happening there? And then just about the time we were thinking that was not going to be broken, here comes 117 kilometers. So these are long DX over the horizon links, long. I mean, he said, do you remember how much path loss he said right here?
60.
Yeah. So we're talking about a budget of hundreds of dBs here. And yet we're making these contacts. Well, it can't be free path space loss that's just killing us. It's got to be an enhancement. It's got to truly be an enhancement. So I also noted that at 24 gigahertz, we have some significant distances. And these are just my experience. We've got Al and Paul Sarver at 157 clicks to Sulphur, Oklahoma. Got me and Al at 194 down to Steve's country, Purvis, near Dublin. An old microwave site down there that has a fly swatter up about 500 feet. At Horizon is at least 20 miles away. It's just beautiful. It's just a little gray trail that might look like low mountains out there. And then W5LUA and and Dave Robinson WW2R at 542 kilometers. Now that is obviously, some bending going on there. And there's many others. These are just the ones I'm throwing out there. This is a regional look at things. I know we have people on here with experience at these distances from other parts of the U.S. and Canada, maybe from Europe as well. So this is just my experience, and I've been dying to be able to understand this for a while. And we wrote emails to Joe Jureka, our meteorologist. We showed him the SKU-T plots and said, is this what we think we're getting? Is these low-level ducts or higher-level ducts, or what could account for this? Well, I have had to encounter artificial intelligence at work. And in order to be competitive, our company has decided that it's an important thing to enroll in. So spend a few $100,000, get a contract, bring it in, train the developers, train the administrative people, put AI to use. So based on what I'm having to experience at work, I opened a private account. It wasn't very costly. And so I just started with this very simple question. Using SKU-T plot data and other weather data for November 1st, 2025, that should be significant to you, Scott. What would account for a 47 gigahertz radio contact using continuous wave mode from Van, Texas to Allen, Texas? Well, actually, contact was made with Al at 47, but 24 with you. And it came back and said, okay, now I have enough information for a thorough analysis. Let me put this together. This is an excellent and highly technical question sitting at the intersection of millimeter wave RF propagation and atmospheric physics. Here's a comprehensive analysis of what the SKU-T data and weather conditions on November 1st, 2025 would tell us about that 47 gigahertz CW contact. Summary. The 47 gigahertz CW contact from Van to Allen on November 1st, 2025 was almost certainly enabled by tropospheric ducting, specifically a combination of subsidence inversion from a post-frontal high-pressure system showing up on the SKU-T as a mid-level warm nose between roughly 850 to 700 millibars with dry air aloft and moist air trapped below. That morning, I had this jacket on and was just shaking. I was so cold, and it was so moist that it was the dew was forming on the dish. That's how humid it was. And the last contact we had was like that. And I told my partner that day, ain't nothing going to work today because it's way too high humidity. And that's where we made that first contact, was in that moist air. Flawed. Number two, nocturnal radiative inversion over the flat, dry Blackland prairie terrain, creating a shallow surface-based or near-surface elevated duct. The very type that preferentially propagates millimeter wave frequencies. Who would know that? I wouldn't know that. 46. I'm thinking, this is a squashed, narrow waveguide that's not high up in the air. 47 gigahertz, sitting in a parallel atmospheric window between 24 gigahertz water vapor and 60 gigahertz oxygen absorption peaks, reducing gaseous path loss enough to make the contact viable. And 4, flat terrain along the entire path with no significant obstacles to disrupt the duct geometry. The SKU-T for Fort Worth, Dallas on that date would be the key diagnostic. A clear temperature inversion layer, the red line bending right with altitude, wide dew point depression aloft, dry air, calm winds, parentheses, wind barbs show light or calm, and a stable thermodynamic profile. All the signatures of a ducting event in progress. Adding additional context. Okay, so I was happy with that. I thought, we finally got confirmation of what took place that day.
Was that 4 reasons?
That was four basic reasons, but it gets a lot better, Wes. Okay. It's going to get so much better.
Trying to understand
Right, it's going to get so much better. I was pretty jazzed by the first response, and that took 1 minute. to 1 minute. It had collected all that, compiled all that, and spit it out as the findings. So I said, well, why don't we just add some more analysis here? Because we got a handful of contacts between me and Al and Scott and John, Jerry? We've got a few contacts that we could throw in here. So I went on and added another 47 gigahertz contact that we had from EM13 Echo India, Ball Knob Hill. That's the name of it. That was later in the morning. It wasn't real late, but it was a little bit later. And then a 24 gigahertz contact with Scott from the same location where we had a 40. Anyway, I added those, and it came up with a composite table of comparisons. And that's what's displaying on the screen here now. So it began to evaluate where there was alignment and where there wasn't. And one of the contacts revealed that it was not a low-level duct on 47. It was a higher-level duct. And it gives the reasoning for that and the proof here. So I said to myself, this is all fine and good, just going through this and spending my Saturday morning just reviewing and reliving and memorializing those memories and all that. But what could we do with this? I said. So I asked this question. Well, I didn't ask. I told it. By now I knew you could tell it. Anything. Create a predictive model that would predict enhanced propagation at 47 gigahertz in the North Texas area. And it took 1 second and came back and said, let me read the front-end design skill before I build this. Now let me think carefully about what the model needs to do and then build it. The model needs to pull real-time weather data for North Texas, score conditions against the known propagation factors, inversion strength timing, absolute humidity, surface dew point, wind, sky covers, subsistence cap, and show a clear prediction with the reasoning behind it. Okay, do it. Run. And so the first model is shown here, and its output was to here's what the model will do and how it's built. Live data, current ASOS observations from the IEM network every 10 minutes. You can switch between KDFW, KTKI McKinney, KADS Addison, or KGPM Grand Prairie to get the reading closest to your path. The 7 scored factors will be, and they are weighted from the physics of your 3 confirmed contacts. Keep that in the back of your mind. The 3 confirmed contacts will be a weighting factor. To absolute humidity will contribute 26%, wind speed 18%, sky cover 15%, time of day 14%, T to TD depression is 11%. Season of the year, 9%. Pressure trend, 7%, rising or falling. Duct mechanism diagnostics, 3 independent subscores will tell you which duct type is likely active. Nocturnal radiative, which was the November 2025 mechanism. Subsistence cap, the June 1st mechanism, or moisture enhanced. Score interpretation, greater than 80 will be high confidence. Activate the station. Greater than 65 worth monitoring. And then the live 47 attenuation estimate in dB per kilometer is calculated in real time from the observed absolute humidity. So this is the first model. This is about 9 o'clock last Saturday. And I was like, okay, look like we're headed in the right direction. But a lot more has happened. So once we got the first looks here and then built an app over it so that it would display the results graphically, I started to feel like we need to expand this to a 500-mile radius. We're going to have to pull in all these other SCUT plots that are balloon launches from around the area. We're going to have all these other observations, which are basically airport, real-time data in terms of pressure rising or falling, and temperature, relative humidity or dew point, and sky conditions and stuff like that. It's coming from airports. And we're going to have to add more data into the model because we've only got 3 in the calibration set right now. So it has evolved into a whole lot more than that. But this was the realization of what we call now the propcast model. And so this is just a picture of the first time I took a picture of it. And, well, I'd like to enlarge that, but it doesn't seem to work for me like it did for Keith. There's a lot here, and I would like to just take a minute or 2 or 3 and actually call the app up in real time and just scroll down through it briefly. Now, each one of these applications are going to end up being 3. Each of them deserves a presentation on their own, at least one, because there's just so much detail in here and so much potential and possibility that I can't cover it in the time we have today. But this is a teaser to let you know we're working on this. There's several people involved, and we want to end up with something that is much larger than just the Texas regional area. So I'm going to cover the rest of this, and then we're going to go, when we get done, we're going to go to the application itself in real time and run some of these apps and scroll down. This page is very, very, very long. It's got a lot of data on it. What you're seeing here is just the very top of the page. So propagation forecasting, that's what this one's about. So I said, well, if we have propagation forecasting and we have real-time atmospheric data, why don't we create a link budget analysis? That would be cool if we had, something that was on the propcast and it said, you wake up, fool, you might need to call into work and go get a hold of Al and plan a trip out to East Texas today. Well, then what I would like to know more granularly, because that map that I just showed, this is not the Hepburn map. This is not Hepburn. Oh, I guess I'm going the wrong way. No, going right. This is not Hepburn, Scott. This is not Hepburn. This does not mean because these are green and they're showing favorable 47 gigahertz conditions, it does not mean that you can make a contact from there to there or even to there. There are basic physics, laws of physics that will prevent that from happening, but it is suggesting that conditions are good right above this airport. And so if you get a cluster of those and they're, within 100 miles of each other, now you might have something. But if you think you have something, then you need a real link budget analysis. You need to say, all right, I'm planning to get in my car and drive 200 miles, and I'm going to get Al up, and then I'm going to ask him to get on the air. What's it going to be like in 6 hours from these 2 grid squares? And I need a tool that will do that so that I have some confidence in it, especially if it works. And we start compiling successful contacts as a result of being motivated by these apps. David, you have a question?
Yeah, just each one.
Yes. This is all free sources. Okay. Mm-hmm. Okay, well, it's an idea that we can explore. I do wish we could fill in some of the blanks. I do know that individuals, people everywhere now have data collection on the roof of their house. We have another associate that is working on a program that just collects that information. And anyway, let me continue here. Yes. Yes, that's why those are all green with that slant. Yeah, that was last weekend when we had the temperature drop. It did. It clearly showed the gradient, which is, it's not really too much science to that. I mean, you could have your TV going and show the guy showing you the line, and then you could have this thing and you go, well, they line up. So then, I'm back to this link budget. So I said, I told it, I want to do a link budget analysis. So it said, okay, I told it, your inputs are going to be Maidenhead squares The frequency, I want it selectable between 24 and 47 or 47. And the mode, I want it to be CW or SSB. As far as digital and WSJT, if that is something you're curious about, just add 20 dB to whatever it comes up with, What it needs to compute: path, distance, and bearing from the two grids. Find the nearest weather stations to the path midpoint from live observations. Free space path loss at the selected frequency. Compute gaseous absorption loss, which is ITU R.P.676 simplified, times path length. Duck/enhancement probability from the Propcast working engine, a realistic signal budget with estimated margins, and a success percentage derived from score plus link margin. So we're going to leverage the pieces of work that's already gone on in the engine that's on top of that calibrated model. Still only 3 contacts in there, but we're going to leverage it and make use of it in another new app called Link Budget Analysis. Just remember, I don't want to get in the car and drive all the way up here to David's location or, McKinney or Honeygrove unless I've got some kind of confidence that, this is worth the drive. It takes a long time to do that. The final core design spec was on this page. I'm not going to read all this. And I did say I want a T plus 6 hour forecast. So I want a current. This is the way it is right this second. I want a T plus 6 and I want a T plus 12. But I hadn't added that at the time I wrote this slide. But we did add T plus 12. That way, I don't have to get up at 1 a.m. to see what it's going to do at 6 a.m. I can just check it at 6 p.m., understand there's some differences with a 12-hour forecast versus a 6-hour forecast, but work with a 12-hour forecast. This is what came about. The NTMS millimeter wave link budget analysis page. And this page, again, is very, very long, goes into great depth, starts off right here with such information as, what are your 2 grids? Your 2 grids go in here. What frequency? 47, 24. How much power are you running? What's the antenna gain? What's the receive antenna gain? What's the feed loss? What's the noise figure? And then what are the altitudes of the 2 antennas? And then I had it add something I call one wave fudge factor, which is perceived.
It's a bigger number.
It's 6 dB. For Jim, it's 3 to 4 because I got 2 years on him. And just the slightest little, wiggle of some kind with the dish, you're out of business or you're in business. So I just wanted to be able to plug that up and add 10 dB or something and then see the result, the margin, the expected margin. In other words, the number of dBs above 0. Hopefully it's above 0. And then understand what kind of fudging I had put in here. And then it's going to just ask you to click that button, Analyze Path. And if we have the time, we'll go real time to that and take a look at a couple of things there. Again, each one of these needs its own presentation. This one is very in depth, and we've added the SKU-T plots now. They're displayed at the bottom of the page along with a breakdown for those of you that don't want to look at a SKU-T plot. And the SKU-T plot actually has the inversions graphically represented with a light gray band to show you how thick and thin they are. So then I said, well, what else is missing? And I started thinking, how do we get more data into this thing? And what's the right thing to do? I can get a hold of Al and get a hold of some other folks and say, can you list your contacts for me? I can look at the ARRL DX records and I can find, where those records are, when they were made. But the exact time's missing from the ARRL DX roster. And the exact time of the contact turns out to be very, very important. Mostly because if it's at dawn or just after dawn, Greg McIntyre, as you've always said, that's the time to do the thing. And it turns out to be exactly right. And as soon as the sun is up, it's starting to heat the earth and destroy whatever is above it in terms of what we like, which is that duct is going to fracture and the wind's going to come up, it's going to fracture more, and it's going to dissipate, unless it's just one hell of an inversion that it can withstand the daytime and possibly the nighttime. And we found some of that in the data where it persisted for 2 days. Now on VHF and UHF, we know it can linger around for a long time. And you guys are, we're talking to the guys that have worked it. And so you know that that can happen. So I have solicited contact information from several people. That information is coming in and I'm processing it. I got Barry's information. I think yesterday I gave it to the engine last night, and it ran a full analysis on Barry's information. It said, we need to know how high his antenna is. So I had to ask Barry that, but that information has not gone in the model yet, and it probably wouldn't until we have the apps figured out by region. Barry's going to be what we're going to call the Midwest region, as well as Tony. So I'm putting this information in, but I'm thinking, how can we get folks to just do it without us doing it? So I said a historical analysis tool will be helpful, not just for enticing others to participate, but also somebody new that comes along and says, I see you got this thing. I had a contact last year on 10 gigahertz that was 250 miles. How is it that I did that? Well, you can use this tool to do that. It's about looking back, not looking now and looking forward, but looking back, and says, how did that happen on that day? And Scott at lunch gave me a time and a date and a frequency when something unusual happened. And if we have time, we'll just ask the engine to give us the analysis on that. You'll get to see it. Okay? So I said, I want this historical analysis tool, and it's going to, do this and this and this. It's going to have historical observations, surface obs panel. It's going to have an atmospheric refractivity state calculated. It's going to have propagation mechanism analysis determined, or it's going to have it identified. The path loss budget will be there, and the contextual summary. By God, the thing in plain English that tells us how it was that the contact occurred. That's all done by this tool. And it is called Prop Analyzer. And here it is. And all that a guy needs to do here is supply the 2 grids. They don't have to be 10-digit, but it's better when you can. Because this thing knows about obstructions. It knows what the path looks like. Scott, it knows if you were transmitting uphill. It knows, and it calculates that. That's a Fresnel zone obstruction when you're transmitting uphill. It clearly is a Fresnel zone negative. So here we got 10 gigahertz on this, so you can pick 10, 24, 47, put the 2 grids, put the date, the exact time, and click Analyze, and it'll do the rest. Now, if I got some information from somebody in Texas and they said, I want to give you this information. Well, if I had this tool built where they could put it in and they could benefit from putting it in, then I'd just tell them, go to this link. You need to know how to do it. Go to this video and it'll tell you what you need to know. I mean, it's pretty simple. There's like 6 things you put in. And then have it optionally display a button that says submit to the propagation prediction engine. And that would put it into our engine. It put it into calibrated data. So if it's a Texas station that's going to do that, that will end up in our regional calibrated data, which could make a difference. Now, I've gone through a lot of thinking on this, and I got a lot of other slides here, but basically there's questions to be answered, and I need the experts to help determine what those answers are. But let me just finish reading this before I get carried away. Collecting more 10, 24, and 47 gigahertz contact information input to the model engine. This is known as training the AI tool. It's training the AI tool. It's training the AI tool. You ever notice when you're driving and the person in front of you goes way over to the fog line? What do? You go right over to the fog line. You're being trained, unconsciously, consciously, you just go. You suddenly go, whoa, why am I doing that? I'll just come back and get in the center again. But that's training, and this is what we're doing with the AI model. We give it more information, but we got a couple things to be concerned about. One, for sure, the data quality. All it'll take is one 47 gigahertz contact keyed in at 500 miles, and the poison gets introduced. Now, is it going to weight it down so bad that everything goes wonky? Probably not. But I think guardrails are important, and we found this out at work without giving you any proprietary information. I mean, you got to be careful because it makes mistakes. It does just what you give it. And if you give it some piece of information that's way out there, that's going to infect your data. And the problem with AI and other things is, when you're doing a calculation on your calculator and you get it really effed up, what do? Clear. And you start over. Well, now I notice, my iOS now has a back button. So if I divided by the wrong number, I meant to put 0.003 and I put 0.3, I can back up and it just erases that. Well, with AI, it ain't so easy because it's already gone way down the road, and you've got this huge data set that you guys have helped, and we've built over 2 years, 3 years, and it's got all this refinement in it. And then somebody drops it in the punch bowl, so to speak. And you go, oh, crap. Well, sometimes you have to just hit reset. But see what that would do to us? We'd have to have a backup plan. Like everything that Barry sent, everything that Al sent, everything that Tony sent, everything that everyone sent is sitting over here in a journal. So that if we ever have to reset the database and tell it, get rid of it, disregard it, kill it, delete it, but we could refeed all of those transactions and get back to the right state. I do that for work all the time. I'm sick of it. I really don't want to have to do that. So, I mean, one of the things we can do is just do a set of validations that, first of all, you got to put both call signs in. You can't invent a contact that's anonymous that you haven't at least claimed your side of it. But our community is so small that if each person that has inputs here puts in both call signs, then chances are good we got that part right. Now, the distance, possible propagation method, date, time, season, those all things are going to be evaluated by the engine. And if it don't make sense, then it's going to have to kick it out and say, somebody better manually review this. So I think those are the minimum guardrails that you have to put into it. So collect more data, open up a way for operators to input information themselves, using the prop analyzer as a basis, enhance the app to have an optional add to predictive model switch and button, create the add interface to collect key information required for, number one, data quality, we just got through talking about, 2, accurate modeling by the engine. That touches several things because, we're still trying to determine the geographic areas involved and the different propagation methods that are involved, because you can't put rain scatter contacts in with tropo. That's just like infecting each other. I've decided to just throw out rain scatter because we've got enough predictive measures for that. Just watch the news at night. You can tell when the bad storms are coming because if they mention hail, you probably should get your rain scatter credentials updated and start watching rainscatter.com. But we don't have these other predictive measures too well yet in these other areas. Create the add interface to provide immediate value to the operator. I think in the wildest of ideas, I could think of, informing Scott, who's just put in some information, something valuable to him. Maybe all of the contacts we've evaluated so far that had him as one leg, at the touch of a finger, he could see what those, how those were accomplished, and we might be able to provide some kind of a prediction for his area for the next 60 days. I don't know. I don't know until you ask. Expand this. Okay, right now the scoring weights and propcast and the link closure probabilities in the link budget are calibrated against our 4 contacts. We did add one more. Al's long distance contact with WW2R on 24 gigahertz. So now we have 4. With community data, we could do something more rigorous. For each new confirmed contact, we could know the path length, frequency, season, time of day, atmospheric conditions, including skew T-plots. You could compute what the effective duct enhancement must have been to close that link, then build a statistical distribution of duct enhancement versus those atmospheric parameters. The model becomes empirical after you do that rather than physics. I like that. That's getting out there, but I like that. So our initial taxonomy at this point is to characterize these different propagation mechanisms, or I think that's the right word, mountaintop line of sight. That's got to be a category all unto itself. We'll never have mountains. We'll never have mountaintop LOS in Dallas-Fort Worth. Nor will they have them in Cleveland. Nor will they have them in Winnipeg. Have a classification for lake/coastal. These might have to be separated, but I think they would. There is a phenomena over large bodies of water like lakes as versus coastal that yields particularly interesting propagation effects. I've taken rain scatter out. It was on this slide when I wrote it. Fixed/rover enhanced tropo. We do a lot of that here. Implicitly, the baseline fixed station contacts we already have. Each has a fundamentally different physics regime, and the model weights that matter are completely different between them. It's totally different between a mountaintop line of sight that's nothing but free pass loss and some gases and pointing, and compared to our Flatlander experience, where we're over the horizon at 2 times the radial horizon, which is 50 miles. For mountaintop LOS, the dominant variables are terrain clearance, I just said this, atmospheric gas absorption, and antenna pointing. Ducting is largely irrelevant for the mountaintop line of sighter. The model for this setup is almost purely ITUR P.676, gas loss versus plus frontal clearance. Our existing 4 contacts are not useful calibration data for this regime. So they can't benefit from us unless we learn something different. Maybe they do get ducting in the San Fernando Valley. I would imagine they probably do. So, if I don't know how to deal with that right now, that's where, some of these questions come up as well. How are you going to deal with mixed propagations? All you got to do is the guys go up on a mountain, they got one, or they can stay in a valley when the, duct is there. For lake and coastal, the key variable is the evaporation duct over water. Over the Great Lakes and California-Hawaii paths, the duct is remarkably stable and predictable, and profile decreases sharply over cold water, creating a near-permanent surface duct. And the California-Hawaii community has their own models tuned to that specific geometry. Their data would calibrate a water surface evaporation duct layer that our Texas contacts simply cannot inform. For rain scatter, and it goes on and on here, I'm going to throw that out. Although it does have this mention about the sweet spot. Too light a rain, there's no scatter. Too heavy, and the absorption dominates if your signal's traveling through it. Community involvement. We need better model. Better model will come. More successful contacts are predicted. Operators trust the tool. More contacts attempted during the predicted windows yields to more confirmed contacts submitted. Yields model improved. So it's the nice wheel of production and improvement. The key is that each successful contact submission carries its own validation. The atmospheric data retrieved at that time and place either supports the mechanism or it doesn't. A submission where the ASOS data shows 20-mile-an-hour winds, unstable air, and wide T or TD gap claiming a 300-kilometer 47 gigahertz duct contact gets low confidence weighting automatically. I say it gets pitched out. It just goes over here into quarantine, and somebody has to look at it and say, did you mean this or did you get the time wrong? You know, it could just be the time. The physics is self-policing to a significant degree. I call this the long arc. Right now, we have 4 data points, all in one geographic corridor and one climate regime. 2 or 3 years of community submissions across different geographics and seasons could give us enough data to start answering questions that notably in the amateur microwave world that nobody in the amateur microwave world has good answers to yet. We just know it happens and we luck into it. Honestly, I mean, if you're on VHF, you got some tools and that happens and it's a happening thing. Meteor scatter, same thing. You know, we could talk about the other things that are highly successful, but at 47 gigahertz, we don't have that. We do not have that. The military might have it, but we don't have it. Nobody has good answers to yet. Things like what the minimum atmospheric signature is that can support a 47 gigahertz duct contact, or whether that's a seasonal pattern to boundary layer inversion contacts outside of Texas, or how the required duct strength scales with path length. Novel empirical work. That's what I want to do. And if we spend 2 years at it and it don't work and it falls flat on its face, then we can't say we didn't have a high goal and we aimed for it and we tried. Here are the next steps in my mind before designing the database schema or touching any code, because we will be using a free database that's available, and there's a number of other free components that I'll have to incorporate. Before designing that or touching code, it's worth nailing down the submission flow from the operator's perspective. It's what I do at work. I think I know what you want, but I want to talk about how you're going to give me that information and how pretty you want it to look. And, you know, how do you want to be rewarded when you have done this? Of course, I don't say those words out loud. I just work them that direction. What does someone actually enter? What does the app retrieve automatically? What does the validation look like? And what do they get back as confirmation of their contribution? Getting this interaction right determines whether people actually submit or whether it's too much friction. And this flow also defines the data schema more clearly than starting from the database side. Here's some other homework I have. Submit VE4 MA 10 gigahertz contacts that have been analyzed. They've already been analyzed by the engine. I've given that feedback to Barry. Submit to W5LUA 10 gigahertz contacts. They've been analyzed by the engine. This morning they were analyzed. Submit to K8ZR 10, 24, 47, and 78 gigahertz contacts. So Tony's going to stretch us into a new domain. Using SKU-T plots and surface observations, determine how many potential 10, 24, and 47 gigahertz ducting events have occurred in the few months that appear to be prime windows. I want to ask it this today. I won't do it here because it'll probably take it 10 minutes. But I want to say, Al, how many potential 24 and 47 gigahertz contacts have occurred in the months of May and June and September, November in the past 24 months?
And how many have we missed?
How many have we missed? I want it to give me the facts. I want to have it. It has to be rock solid. And then we're going to have a number. It might be 1 or it might be 50. And then that informs me that you're going to have to, when you retire, this is going to have to become a full-time thing. You know, you're going to have to start paying attention. And it might need that we need to make the thing just tell us, you know, there's something about to happen, or tell Tony there's something about to happen, or tell multiple operators, you know, something about to set up maybe for you and this other guy. I don't know. I don't want to limit this. It's at work. I've gotten to where I just try not to let myself think about solving a problem anymore. As soon as I have the problem pop up, If it's something I've done 100 times, that's one thing. But if it's something novel or unique, I think for a moment, is this something I need to go back over here and ask a question?
Let me ask what something. The concept is you're collecting on the able to build your inference engine for your system to work. What if instead you put a bunch of calibrated receivers around, or even just one set, so that you're constantly collecting data between 2 points and feed that back into your system?
You quit broadcasting.
You know, like whisper?
Here's the end.
That's the transmitter, right?
And there's a receiver.
Where's the receiver?
That man on the end.
No, but you're making him work.
I know, but you know what those 47 gigahertz rigs cost?
I know they're expensive. Don't start there. Start somewhere else.
Well, that's that.
And I'm not.
I bet.
Let's start with one to find out if the concept.
I think just well, I mean, we can build a receiver that just sits there automatically collecting data.
Got beacons at
Not at 47. Yeah. No, I think we're interested in anything that you don't have other tools to predict and analyze the data. And we really don't have it at 24 and 47. So I thought about what you're saying is, could we stage autonomous or automatic receiving units that would collect this information? It's costly. We've already understood that it's a little difficult to even find a place to put a beacon to do the transmitting. Or maybe it's just that it's taking longer than we'd like.
Could you run like a whisper beacon?
Well, believe me, at 47 gigahertz and 50 miles, it's a whisper.
Yeah.
It is.
For work that can transmit everybody's listening and comes back.
Yeah, the concept.
Showing where you're getting to. Running a 10 megahertz receiving system with, feeding back into the network to look at changes in the ionosphere. And it's the same thing, but you got to have, if you want scientific data, you have to have something that's fixed that you've measured and then leave it there, collect it that way, I think.
Well, around here though Steve is way far away. Be great down in EM11, where you're at. That would be a nice place for a 10, 24, 47 gig receiver. But up here, I monitor Greg Beacon all the time, and it's there, same signal strength, doesn't waver too much. So it's almost like stations have to at least be some distance apart to come on or get the data that would go into this program, right?
And that's the thing I was worried about, is if you're only going to know that one path that you're looking at, unless you have more receivers. But if you start with one path, my other thought, if you're listening to you talk about this, is such a complicated issue that you almost need to have like a separate working group within NTMS and use the Zoom thing that we're paying for, that you got time window, set up a once a month group session and talk about how to expand it, how to explore what's possible.
Well, I really don't have a patience to do very much of that, but I do recognize that I need more thinking power in it, and I think it needs to come from outside of DFW too. There's experiences that other people have that have been doing it just as long as the people in this room that may bring. I don't need to tell you, Bob.
Well, that's why the Zoom thing work well.
They bring their own. Yeah, I think it's good, but I think I'm going to keep moving with what I know I can generate to get the data into the model as quickly as possible, so that May is coming up soon and June, and that seems to be, based on the results so far, that seems to be the spring, summer prime time for ducting to set up for 47 gigahertz and 24.
I have a lot of ideas. My ideas take up my time badly. And now when I start working with AI has become like my friend, my buddy, sitting there with me. I can ask, hey, buddy, what do you think about this build this receiver and this transmitter? He comes up with all these other ideas. So now my ideas have gone up exponentially, that I have to chase because of AI.
The problem with too much information is nothing gets done because of overload.
We can, that's right. That's an interesting thing that's happening that I'm sure other people are seeing as well. Yeah, great answers back.
It's interesting. He's using past data to predict the future.
Yeah.
And I think, why can't you do that in the software?
You can. You can. Yeah. So I want to have time for the people in our audience to ask questions, but I want to show this. I'm not going to spend any time here. I'm just going to scroll the page. So let you get a taste of it. These links, I can publish these. They are all apps that are on the website. You can see that it just refreshed just a moment ago. You saw the dots come up, and there is this is a 500-mile radius. We can reduce this to 200 miles by clicking this button, and there you go. We can select individual observation points by in the upper right hand. I might not be able to see it with the list of participants that's sitting in the way.
Hey, Jim, I had a question. It'd be nice if you had state lines there, wouldn't it?
They are there. They are there. They're just kind of crummy. Well, I'll try to improve that, but this is Texas right here. This is boundary for Texas. This is Kansas as far as it goes. This is Missouri. This is Arkansas.
Where's the panhandle?
Well, it'd be right over here.
Oh,
I'll take it as a thing and see if I can't. Just for you. I'll see if I can't. Yeah.
I like the way you minimized Oklahoma.
Yeah. Now, see, when you get down here, if you want to have something to laugh about. So right here is the Texas. That's the Rio Grande border right there. Kind of a jag. And then here's Louisiana. This is all the Gulf of Mexico right here. That's why there's no reporting stations out there. Mm-hmm. All right. And then we can go down further. These are the 5 top reporting stations across here. And then the calibration data and the physics explanations are, if you click that button, you will see here's the 4 cards. I'm going to change that to where they're just row over row because we're going to have hundreds. But those are the 4 cards that represent our calibrated data. And here is the physics over here. You can go look at that and play with it if you want. Then we go to the link budget, which was the second one we talked about. Here are 2 grids. Now, a word of explanation on the grids. The grids represent the contact in November that we had when me and Jerry went to EM22 Fox Mike, and we worked Al on 10. Al said, go to 47. We went to 47, worked him with signals to spare. And then I think, Scott, you worked Jerry on 24, and he was elated. And then I worked you on 24. So it was just a really great day. Some people earned VUCC that day. And so this comes loaded with that contact in there. So you can put any grids you want in here. But if we just analyze this path, we've got some parameters as far as power, antenna gain, so forth that I mentioned before. I'm not going to go over it now. We're not particularly care if it's accurate. There it went out. It did the analysis. It starts with all these metrics. There's the path itself and the reporting stations. So this is Greenville. This is McKinney and so forth and so on. That's Tyler. You can see the TY in the name. And then we come down and there's a path profile. This has been scaled according to the height of the antennas. You can see the Fresnel zone is a lighter colored picture. This is the effective terrain. This is a flat earth projection, like you can pick between on, hey, what's that? But there's some information up here as far as the diffraction losses, and so already computing that. Now here's the percentages down here. The 15% on the far left, that's your chances right now. Just stay at home. Get out the popcorn. The middle percentage is T plus 6 hours. The right hand projection is T plus 12 hours. So again, kind of a deteriorating accuracy is the right word. It's not going to be quite as accurate in 12 hours because things can happen. But 12 hours from now is 4 in the morning. It could possibly have 15%. Right now, I don't have link margin for these projections, but right now you'd be looking at 7.1 dB link margin. That's not enough. That's why it's scaling it at 15%. Then here's all the other metrics, the propagation factors. Here's the latest SKU-T. There is an inversion indicated here, but this one would be now 9 hours old. So you see this light gray band, that's an inversion right there. And then there are, that's it. That's the only one there is. And this sounding interpretation, for those of you that don't like, these SKU-T plots, it is giving it all right here. No duck layer in the profile. Standard refraction expected. And so forth and so on. Then we can go up here to the final one, which was the analysis. I don't see it here. It is the link analysis. So I'm not going to try to dig it out and find it, but I should. Well, I said I would, Scott. So it's not the link, it's the millimeter wave. Let me cheat and look at my phone for a second because I've got all those on my phone. Any other questions from the group? Yeah. Well, this here is a standalone app that I wrote over the engine that's up on our website. I also have a Windows desktop version too. But the engine and the analysis and all of the discourse that we've seen is all coming from a private personal account that I opened with the AI engine. By the way, that people have asked about the cost. It's either an annual license at $240, which calculates to be $20 a month, or you can go month to month for $25 a month. Yeah, there is. There is a limit on tokens, and I have busted it. And then it says first it says you reached the 75%, boy, and then it says, I said, when does it renew? It says next Tuesday at 3 p.m. Yeah. And then I hit the limit, and it says you've hit the limit. And I said, how do I get more? They said, click this link, give us money. And so it's just $5. All I gave it was $5, and kind of like what is this NTTA out here? He's paying you for $40, so you can pay in advance. Yeah. Exactly. Okay. Any questions from out in the audience?
I have one suggestion, maybe for getting some of your data set. This is Mark WB5ZDP.
Go ahead, Mark.
Why don't you go back and look at some of the logs from the 10 gigahertz context for some of the long QSOs on 24 and 47, or even 76. You've got at least the 6-digit grid square. You could probably email the people and ask them for more precise locations of both ends if you could reach out to them.
All right. Thank you for that. It's a good idea.
Mr. Webb had a question.
Al?
Yes. I once observed something that might be of interest. For a number of years, I worked portable on Pikes Peak, Colorado over the contest weekend at a 2-foot dish. And I noticed that I could swing that antenna back and forth plus or minus 30 degrees and not see much difference in signal strength. The stuff seemed to be bouncing around and coming from everywhere.
Like Keith over here mentioned at lunch one day that Al works all this stuff off a bird.
Oh,
Thanks for you.
Bird bounce, is that what that was? Okay, I got the prop analyzer finally sorted out, got it figured out here. I'm going to input yeah, I just got in my notes. I probably screwed that up now, but I'm going to see if I've still got that. Do you still have that? Okay, here I got it. I got it. So this I don't have grids. Well, probably EM00.
Look it up. EM10
EM10 Kilo Fox.
Okay, that's like our beacon, only it's 13.
Yeah.
Okay, and what can you give me? Would it be yours or would it be the EM23 something? Well, I know yours by heart. SG, right?
Yeah.
Okay, so we know that this thing happened on the 18th of September, 18 in 2022. And the exact time of day was 1400. Just have to get it all right here. Let me click back into this. All right, I'm going to tell it to run to mama. There it did. All right, so here we go. It had enhanced refraction pre-dawn inversion. The temperature was 74.8 to 2.71.3. That's pretty moist. It's got the absolute humidity here, 19.18 grams per cubic meter, 5 mile an hour wind. Let's continue here.
I gotta go, guys.
Bye, David. Nice to see you again.
Yeah, great stuff, man. This is really exciting.
The factors come in at top propagation score is 95%. The season score, again, lining up with the things that happen during the certain seasons, 98%. The absolute humidity hit, it just repeated that value. Then it's got additional. It's got all the observations at all 5 of the stations at that time, the 5 closest stations. And then it's got a synopsis here, a surface duct, 95% probability surface duct inversion, pre-dawn inversion layer traps 10 gigahertz energy near surface, dramatically exceeding range.
Is this what happened?
Yeah.
Get a ribbon back this way, and all of a sudden, the bodacious CW signal shows up. Nobody knew who it was. It turned out to be Ron. He was S9 plus, and I had a dish 44 feet.
Ron also worked at it and Nina.
Yeah, that was a big one, long one. Going to read this synopsis down here. Again, the surface duct inversion was a 95% factor. Tropospheric scatter, we know about that. Common volume, 85%. Moist layer scattering, 55%, so a lesser degree there. The contact between EM10KF and EM13SG on 2022-09-18 at 8 Central Daylight Time, 1300 Zulu, 344 kilometer gives the direction. Pre-dawn inversion window, prime inversion conditions, fall, optimal inversion, absolute humidity 19.2 grams, high moisture loading, elevated gas absorption, but strong refractivity gradient. Super refracting conditions, A equals 1.55, significantly extend effective radio horizon, and at 10 gigahertz tropospheric scatter provides a reliable baseline mechanism. This path, 344 kilometers, is well within scatter range. So there you have it. You probably knew all that anyway, but there it is in black and white. Now I want to go to the engine. Lots of stuff I'd like to do, but let's get to the engine itself here. And we're going to pose a question. The question was, how important is antenna height to launching into the duct, right? Somebody posed that question here. Ask me that. Okay.
That was a good question.
Now let's ask. How does antenna height, well, it's not a laser beam, but I get what you're saying, and let's add that in here. How does antenna height and, can I use the word dish? Dish elevation. Hard to type when this thing's at this angle, when both wrists have been broken. And dish elevation affect probability of success in launching to waveguide, atmospheric waveguide. This is old hat for you, Bob. This answer alone could take us into a rabbit hole that would take weeks. All right, here we go. Run home. Thinking. Great question. This gets into the coupling efficiency problem, which is one of the least discussed but most important factors of millimeter wave tropo work. I knew it. Here we go. 3 weeks. Antenna height and elevation angle, coupling to atmospheric waveguides. The core problem, a tropospheric duct is a physical waveguide layer in the atmosphere, typically 50 to 500 meters thick at some height above ground. Your antenna must illuminate that layer at the correct geometry. 2 independent variables control this. 1, physical antenna height above ground determines whether the antenna beam physically intersects the duct layer at useful path distance. That was a soft answer. 2, dish elevation angle determines the vertical angle of the beam, which combined with height and distance sets where the beam axis crosses the duct. Those interact, and getting both wrong means launching energy above or below the duct entirely. Oh boy. And it's going into the geometry here. That's right. Yeah. And they did that at the Great Lakes too. I believe Tony will tell us that is how high up on the hill they were. That the ones that were higher were no goody, and the ones that were lower were worky. Yeah. So the geometry, I don't know if I have enough time for this, but for a surface duct base to ground, top 50 to 200 meters above ground, the coupling requirement is straightforward but demanding. The beam must arrive at the duct lake at a grazing angle, duct layer at a grazing angle, typically less than 0.5 degrees for efficient coupling into a surface duct at 10 gig. Above that, above about 1 degree, the signal largely passes through the duct ceiling rather than being trapped. For W5LUA, it knows you. Well, it's based on our models. It already knows your call sign. It knows Barry's.
It's got your credit card.
Yes. I didn't tell him his name, but I'm sure he could look it up. For W5LUA at 70 feet, it knew that because I told it this morning. 21 meters, aiming at a duct top of say 150 meters above ground. It gives 3 quotients. At 100 kilometers, elevation needed is the arctan of da-da-da-da-da. That would be a grazing blow. At 300 kilometer, the elevation it needed, well, let me give you the elevation for the first one, 0.074 degrees. And you hit sub 1. Well, that's sub, yeah, that's going to be sub 1. That's 3/4 of 74 thousandths. And then for 300 kilometers, you need 0.025 degrees. That is the excellent entrance. And at 500 kilometers, Earth curvature dominates. Target duct is geometrically below the horizon. Earth curvature drops the apparent horizon by about 1 degree per 300 clicks at the surface. This means for paths beyond 300 clicks, a surface duct contact requires the duct to either be elevated or the Earth's effective radius to be significantly extended by the duct itself. K factor over 1.33. And this goes on and on and on and on and on. Okay. Yep. I know we all have, some of us have long drives and we need to go. Anything from the a crowd yet out there in Zoom land? Any other comments?
Great work, Jim.
Hi, Greg. Good to meet you, Graham. All right, guys, I think we're ready to adjourn. There is a VE4MA mention in here. It's talking about maybe we input this into the model. I got to think about that. Elevation, angle, and duct height are the critical coupling variables, not antenna height per se. Beyond the threshold of clearing local obstructions, the fact that VE4MA at 50 foot flat prairie and W5LUA 70-foot suburban Dallas both achieve similar range classes confirms this. The duct geometry is the dominant term. Interesting. All right. I think that's it for this month, folks. Thank you for attending, and we'll see you again next month.
Thank you so much, Jim. Great job.
Thanks. Great
Thank you, Barry.
Thanks, guys.
Thank you, Barry.
That's smart. Barry. Bye.
Wow.